Millions of years ago, scientists dig deep into the Earth and find strange things like life inside rocks, lost continents, and events without clear causes. Fossils show creatures from long before humans. But what if there is more? Something older than we remember, buried far below? Could an ancient civilization have existed long before us, now completely forgotten? We know more about distant galaxies than we do about Earth's deep past. What else might be hidden in the layers beneath our feet? Defining civilization is a complex undertaking, especially when considering the possibility of advanced forms existing millions of years before humanity. It requires moving beyond our human-centric view to establish criteria that are universally applicable yet specific enough to differentiate a true civilization from merely complex biological life, or even sophisticated animal societies. At its core, a civilization represents a highly organized and self-sustaining community, exhibiting significant control over its environment and resources, demonstrating complex social structures, and often leaving a lasting impact on its surroundings. This impact is the key to our current inquiry, a signature that might persist across vast geological epochs. To begin, let us consider the fundamental components that distinguish a civilization from other forms of life. Biological complexity in itself is not enough. An ant colony, for instance, displays incredible organization, sophisticated communication, and even a form of agriculture tending to fungi or aphids. Beehives are marvels of communal living and engineering, building intricate structures and managing complex social roles. Yet these are instinct-driven biological imperatives, not the result of conscious abstract thought innovation, or the kind of cumulative technological progression we associate with civilization. They are highly evolved biological systems adapted to a niche, not societies that invent new technologies or ponder philosophical questions. The crucial difference lies in the capacity for deliberate innovation, abstract thought, and the transmission of learned knowledge across generations in a way that transcends mere genetic programming. Toolmaking is another facet often considered, but it too has degrees of complexity. Early hominids fashioned stone tools for millions of years. Chimpanzees use sticks to fish for termites, and some birds use tools to obtain food. This basic tool use, while important for evolution, does not automatically signify a civilization. An advanced civilization uses tools not just for immediate survival, but to construct complex infrastructure to manipulate energy on a grand scale, and to develop technologies that are far removed from natural materials and simple extensions of the body. It is the systematic production of increasingly complex and specialized tools and the development of processes to create those tools that becomes indicative. Think of the difference between a sharpened stone and a microchip or a complex genetic editing system. A truly advanced civilization as relevant to our hypothesis implies a level of technological and societal organization that moves beyond mere subsistence. It suggests the ability to harness energy beyond direct muscular effort, for instance through fire-water wind, or more advanced means like fossil fuels or nuclear power. This energy manipulation allows for large-scale construction, manufacturing and transportation, fundamentally altering the landscape and the capacity of the society to grow and sustain itself. It is the ability to not just live within an environment, but to extensively modify it and extract resources on a scale that impacts planetary systems. Societal organization is paramount. This involves a division of labor where individuals specialize in roles beyond hunting-gathering or basic farming. This specialization leads to interdependent relationships and the need for complex governance systems to manage these interactions. Laws, rules, and hierarchical structures emerge to maintain order and facilitate collective action. Economic systems develop involving trade currency or complex exchange mechanisms allowing for the distribution of goods and services. Urbanization is a common outcome of such organization, with dense populations living in cities or large settlements, supported by surrounding agricultural or industrial areas. These urban centers often become hubs of innovation, cultural exchange, and political power. Cultural and intellectual development also marks an advanced civilization. This goes beyond basic communication to include complex symbolic languages, whether spoken, written, or otherwise. The ability to record and transmit knowledge across generations is vital, allowing for cumulative learning and technological progress. This can manifest in writing systems, libraries, and educational institutions. Art, music, literature, and philosophy emerge as expressions of abstract thought, creativity, and a deeper understanding of the world. Scientific inquiry, the systematic pursuit of knowledge through observation, experimentation, and rational analysis, is a hallmark of truly advanced civilizations, pushing the boundaries of what is known and technologically possible. Environmental impact is an unavoidable characteristic of an advanced civilization, especially one with industrial capabilities. Large-scale resource extraction, such as mining for metals or quarrying for building materials, leaves significant geological traces. The processing of these materials for manufacturing creates unique byproducts and waste streams. Industrial processes often release specific chemical signatures into the atmosphere, oceans, and sediments. The scale of these operations can alter atmospheric composition, affect global temperatures, or even trigger changes in ocean chemistry. Such impacts can be detectable over geological timescales through the analysis of isotopes, trace elements, or unusual mineral formations. This footprint distinguishes an advanced civilization from animal species which modify their environment, but rarely on a planetary scale. Consider the longevity of a civilization's impact. For a civilization to be detectable millions of years later, its influence must extend beyond the ephemeral. This means building structures with a degree of durability, creating materials that are resistant to natural degradation, or leaving broad-scale alterations to the planet's chemistry or geology. Monuments, large-scale infrastructure, and deep mining operations represent potential forms of lasting physical evidence. The deliberate long-term planning required to construct such enduring features suggests an advanced societal capacity. Distinguishing civilization from highly social animal behaviors is critical. While some animals exhibit remarkable collective behavior and even limited tool use, they do not demonstrate cumulative technological progress or abstract cultural development. Beavers build dams, but these structures are part of an instinctual pattern, not the result of evolving engineering principles or the invention of new building materials beyond wood and mud. Their structures do not show systematic improvements or a history of varied design. Similarly, the complex societies of ants or termites, while incredibly efficient, do not innovate beyond their species-specific genetic programming, nor do they engage in scientific discovery or artistic expression. Their impact on the planet, while significant in some ecosystems, is fundamentally different from the systematic large-scale resource consumption and landscape transformation characteristic of an industrial civilization. The concept of scalability is important. It is not just about a single ingenious invention, but the ability to apply that invention on a mass scale to affect large populations and transform societies. The invention of the wheel is profound, but its true impact comes from its widespread adoption for transportation and machinery enabling cities and empires. This requires organized production systems, a workforce trained in specialized skills, and the infrastructure to support widespread use. A civilization has the capacity to replicate and distribute its innovations across a large geographic area and demographic. The problem of anthropocentrism is a significant challenge when defining civilization for a pre-human context. We tend to define advanced intelligence and civilization based on human characteristics, like bipedalism, complex language as we know it, and specific types of technology. However, an alien or ancient non-human civilization might have developed along entirely different lines. They might communicate through telepathy or chemical signals. Their technology might be biological in nature rather than mechanical or electronic. Their structures might be grown rather than built. The core criteria therefore must be broad enough to encompass these possibilities, while still being specific enough to denote something truly advanced. The key lies in the measurable impact on the environment, the systematic application of abstract thought to solve problems, and the transmission of cumulative knowledge that allows for progress beyond instinct. The role of language and communication cannot be overstated. While not directly detectable in the geological record, a sophisticated symbolic language is a prerequisite for the complex social organization and knowledge transmission that defines a civilization. It allows for the sharing of complex ideas, the coordination of large-scale projects, and the accumulation of knowledge over generations. Without it, complex societal structures and technological advancement would be severely limited. Even if the form of communication is alien, its function in enabling complex societal interactions would be similar to human language. warfare and conflict, while often destructive, also highlight a level of organised societal structure. The capacity for organised warfare defence strategies and the production of weapons indicates a complex society capable of mobilising resources and coordinating large numbers of individuals for a collective purpose, even if that purpose is destructive. Fortifications and battlefields could theoretically leave geological traces, though perhaps less distinct than industrial waste. Art and symbolism go beyond mere utility. They represent a civilization's capacity for abstract thought, spiritual or philosophical inquiry in the expression of beauty. Cave paintings, ancient sculptures and ceremonial objects all point to a culture that transcends basic survival needs. These might be less likely to survive millions of years than a large-scale industrial byproduct, but their presence in a contemporary context is a strong indicator of civilization. The necessity of surplus is a practical marker. A civilization cannot sustain specialized workers, artists, scientists, or complex governance unless it can produce more food and energy than its population immediately consumes. This surplus frees up a portion of the population from direct subsistence activities, allowing for the development of specialized skills and the pursuit of knowledge and culture. Efficient agriculture, sophisticated hunting techniques, or advanced energy capture methods are therefore foundational. This surplus creates the economic base necessary for large-scale projects and societal development. Urbanization and infrastructure development are strong physical indicators. The construction of cities' roads, bridges, water management systems, and waste disposal networks signifies a deliberate and large-scale modification of the environment for human settlement and commerce. These structures, especially those built from durable materials, can leave lasting imprints in the geological record even if highly eroded or buried. The patterns of these settlements, if discernible through geological strata, could indicate a planned and organised society. Understanding the deep timescale is absolutely fundamental when we discuss the possibility of advanced civilizations existing millions of years before humans. It is not simply a matter of a very long duration, but a profoundly different way of conceptualizing time, where geological forces unfold over spans that dwarf human experience and even the entire history of our species. When we say millions of years, we're talking about durations so immense that the Earth itself undergoes transformative changes, constantly recycling its crust, reshaping continents and altering its atmosphere. This relentless geological activity is the primary challenge to finding any direct evidence of ancient life, especially complex structures or technological remnants. To grasp deep time, we must first appreciate that it is an active force. The Earth is not a static stage upon which life plays out, but a dynamic planet constantly in motion, constantly eroding, building and burying. These processes are slow on a human timescale, but over millions of years they accumulate into monumental shifts. Mountains rise and worn-down ocean basins open and close, and entire land masses migrate across the globe. This constant churning of the planet's surface is both a record keeper and a relentless eraser of past events. The concept of geological time began to solidify in the 18th and 19th centuries, with early geologists observing rock layers and fossil sequences. They realized that the Earth's features could not have formed in just a few thousand years, but must have taken immeasurable periods. This realization was a monumental shift in human thought, challenging previous ideas about a young Earth. Charles Lyell's principle of uniformitarianism, a cornerstone of modern geology, proposes that the same natural laws and processes that operate today have always operated in the past. While the rates and intensities of these processes may have varied over time, the fundamental mechanisms remain consistent. This means we can infer past conditions and events by studying present-day geological phenomena. To measure these vast spans of time, scientists employ two main methods: relative dating and absolute dating. Relative dating helps determine the chronological order of geological events without assigning specific numerical ages. It relies on principles like superposition, which states that in an undisturbed sequence of sedimentary rocks, the oldest layers are at the bottom and the youngest layers are at the top. Cross-cutting relationships tell us that a geological feature that cuts across another is younger than the feature it cuts. These principles allow geologists to reconstruct the sequence of events that formed rock formations and placed fossils within them. Absolute dating, on the other hand, provides numerical ages for rocks, and events typically in millions or billions of years. The most precise method is radiometric dating, which relies on the predictable decay of radioactive isotopes within rocks. Certain unstable isotopes like uranium-238 or potassium-40 decay into stable daughter isotopes at a constant known rate called a half-life. By measuring the ratio of the parent isotope to the daughter isotope in a rock sample, scientists can calculate the age of the rock. For instance, uranium-238 decays to lead-206, with a half-life of about 4.5 billion years, making it suitable for dating very old rocks. Carbon-14, dating with its much shorter half-life of 5,730 years, is used for dating much younger organic materials up to about 50,000 years old, far too short for our current inquiry into deep time. The accuracy of radiometric dating methods has been rigorously tested and verified by multiple independent techniques, making them the bedrock of the geological timescale. The geological timescale itself is a hierarchical system that divides Earth's history into eons, eras, periods, epochs, and ages. This scale is constructed from geological strata, and the fossils contained within them providing a chronological framework for Earth's past. The largest divisions are eons. The Hadean eon, from 4.6 to 4 billion years ago, was the earliest time in Earth's history characterized by intense volcanic activity, frequent asteroid impacts, and the formation of the Earth's crust and oceans. Conditions were far too extreme for life, let alone civilization. The Archean eon, spanning from 4 to 2.5 billion years ago, saw the emergence of the first life-form single-celled organisms like bacteria and archaea. Continents began to form but remained small and unstable. The atmosphere was largely devoid of free oxygen. Any life during this time was microscopic and primitive. The Proterozoic eon, from 2.5 billion to 541 million years ago, was a time of significant evolution, including the oxygenation of the atmosphere by photosynthetic organisms and the appearance of more complex single-celled eukaryotes, and eventually early multicellular life. Towards the end of this eon, the first animals appeared, still no sign of advanced complex life forms relevant to civilization. The Phanerozoic eon, meaning visible life, began 541 million years ago and continues to the present day. This eon is divided into 3 eras, the Paleozoic, Mesozoic, and Cenozoic, each marking major shifts in life forms and geological configurations. This is the era most relevant to the question of advanced life, as it is when complex organisms became widespread. The Paleozoic era, from 541 to 252 million years ago, is often called the Age of Ancient Life. It began with the Cambrian explosion, a rapid diversification of animal life, including the appearance of most major animal groups known today. This era saw the rise of fish, amphibians, and early reptiles, as well as the colonization of land by plants and later by animals. Major geological events included the formation of the supercontinent Pangaea. The era ended with the Permian-Triassic extinction event, the most severe extinction in Earth's history, wiping out about 90% of marine species and 70% of terrestrial vertebrate species, a stark reminder of the planet's dynamic and sometimes violent past. The Mesozoic era, from 252 to 66 million years ago, is famously known as the Age of Dinosaurs. It is divided into the Triassic, Jurassic, and Cretaceous periods. During this time, dinosaurs dominated terrestrial ecosystems, while marine reptiles flourished in the oceans. Flowering plants also emerged and diversified. The supercontinent Pangaea began to break apart, leading to the formation of modern continents. The Mesozoic era concluded with the Cretaceous-Paleogene K-PG extinction event, approximately 66 million years ago, caused by a large asteroid impact that led to the demise of the non-avian dinosaurs and many other life forms. This event is highly relevant to our discussion, as it demonstrates the immense power of singular catastrophic events to reshape life on Earth. The Cenozoic era, from 66 million years ago to the present, is the age of mammals. Following the KP extinction, mammals diversified rapidly, filling the ecological niches left vacant by the dinosaurs. This era is subdivided into periods like the Paleogene, Neogene, and Quaternary, and further into epochs like the Paleocene, Eocene, Oligocene, Miocene, Pliocene, Pleistocene, and Holocene. During the Cenozoic, continents continued to drift towards their current positions, major mountain ranges like the Himalayas formed, and global climate underwent significant fluctuations, including repeated ice ages. It is only in the very recent geological past, within the last few million years of the Cenozoic, that hominids evolved, leading eventually to Homo sapiens, a mere blink of an eye in geological terms. The implications of deep time for the preservation of evidence are profound and largely negative for the hypothesis of an ancient civilization. The relentless forces of plate tectonics ensure that most of Earth's surface material is constantly recycled. Oceanic crust is created at mid-ocean ridges and destroyed at subduction zones where it plunges back into the mantle. This means that virtually all oceanic crust older than about 200 million years has been recycled, leaving no record of anything built upon it. Continental crust is more stable, but still subject to immense pressures and transformations. Tectonic forces cause mountain-building faulting and folding, leading to the burial, uplift, and deformation of the rock layers. Any structures or artifacts embedded within these rocks would be subjected to crushing pressures and intense heat, possibly metamorphosing them beyond recognition. Erosion and sedimentation are equally formidable forces of erasure. Wind, water, and ice constantly wear down landforms, transporting weathered material and depositing it elsewhere. Over millions of years, mountains can be entirely leveled, and vast quantities of sediment can be deposited, burying former landscapes kilometers deep. A city or industrial complex might be buried under layers of rock, but the immense pressures and temperatures at such depths would likely turn its components into unrecognizable metamorphic rock. Alternatively, erosion could simply wear away all traces, exposing them to the surface where they would then degrade. Metamorphism, caused by heat and pressure deep within the Earth, can completely alter the original composition and structure of rocks, destroying any subtle features or artifacts within them. Diagenesis, the physical and chemical changes that occur in sediments after deposition, can also obscure or destroy evidence. Even within sedimentary layers where fossils are found, the process of fossilization itself is exceedingly rare and biased towards hard parts like bones and shells. Soft-bodied organisms are rarely preserved. Technological artifacts made of metals or complex polymers would be even less likely to survive given their susceptibility to corrosion, decay, and breakdown by geological processes. Biological activity itself plays a role in the destruction of evidence. Microbes decompose organic matter. Plant roots can break apart rocks and structures. Burrowing animals constantly churn and disturb the uppermost layers of soil and sediment. Over millions of years, these activities contribute to the degradation and disarticulation of any potential remnants. The impermanence of surface features is a key takeaway. What we see as stable landscapes today are fleeting moments in geological time. A mountain range takes millions of years to form and millions more to erode away. Rivers change courses, coastlines shift, and deserts expand and contract. Any civilization existing on the surface would inevitably be swallowed by these dynamic processes, either buried and transformed or completely eroded away. The cyclical nature of Earth processes also contributes to the difficulty. Global climate cycles, including repeated ice ages and periods of extreme warmth, have dramatically altered sea levels and environments. Glaciers scour landscapes like giant bulldozers, removing all surface features. Sea level changes can submerge coastal cities or expose vast areas of former seafloor to erosion. These cycles further complicate the preservation of any continuous record. Considering the concept of a moment in deep time highlights the immensity of the challenge. Even if a hypothetical advanced civilization flourished for 1 million years, a long duration by human standards, this period represents an incredibly short flicker in Earth's 4.6 billion year history. It is akin to a single second in an hour. Finding traces of such a brief existence within the vastness of geological time is like searching for a specific grain of sand on a sprawling beach after it has been repeatedly churned by storms. The probability of its unique preservation without transformation is exceedingly low. The challenges we face in looking back across deep time also provide a sobering perspective on our own future. If humanity were to disappear, what would remain of our civilization in millions of years? Our concrete structures would crumble, metals would corrode, plastics would eventually degrade, and our digital information would vanish. The most lasting traces might be altered mineral deposits, a distinct chemical signature in geological strata from fossil fuel burning, or perhaps a thin layer of unusual geological material marking the Anthropocene epoch. These would be indirect signals very difficult to interpret as evidence of a highly advanced intelligent society without a key to unlock their meaning. Understanding deep time is therefore critical for not only geology, paleontology and climate science, but also for tempering our expectations when speculating about ancient civilizations. It forces us to confront the immense destructive power of natural processes and the inherent impermanence of even the grandest human endeavours over grand scales of time. The vastness of geological time relentlessly erases or transforms most evidence, making the search for pre-human civilizations an extraordinary scientific challenge. The natural forces at play ensure that what persists are usually only the most durable and simplest forms of evidence, leaving behind a heavily filtered and fragmented record of Earth's past. The story of the human timeline is a recent chapter in the vast geological history of Earth, a fleeting moment when viewed through the immense lens of deep time. Our journey from early hominids to complex global societies spans millions of years, but the rise of truly advanced civilization, the kind that leaves a discernible mark on a planetary scale, is a phenomenon of the last few thousand years, a mere blink in the 4.6 billion year saga of our home planet. Understanding this relatively short and recent trajectory provides a crucial baseline for contemplating whether similar advanced societies could have existed long before us. The earliest ancestors of humans, the hominids, began to diverge from other apes in Africa perhaps 6 to 7 million years ago. These were not humans as we know them, but bipedal primates exhibiting key adaptations that would eventually lead to our lineage. Australopithecus species flourishing between 4 and 2 million years ago represented a significant step. They walked upright, which freed their hands for carrying objects and possibly manipulating tools. Their brains, though small by modern human standards, were larger than those of other apes relative to body size. These early hominids lived in savannas and woodlands, often foraging for plants and scavenging for meat. Their tool use was rudimentary, perhaps involving unmodified stones or simple sticks for digging or breaking open nuts. This period was characterized by slow, biological evolution and minimal environmental impact beyond that of any large animal population. There was no organized societal structure beyond small nomadic family groups, and certainly no lasting architectural or industrial footprint. Around 2.5 million years ago, the genus Homo emerged with species like Homo habilis, the handy man. This marked a significant shift as Homo habilis began to intentionally flake stones to create sharp-edged tools known as older one tools. This was a cognitive leap, the deliberate shaping of raw materials for a specific purpose. These early humans still lived in small groups foraging and scavenging, but their improved tools gave them an edge in processing food and perhaps defending against predators. The brain size of Homo habilis was notably larger than Australopithecus, indicating increasing cognitive abilities. Their lives were dictated by the immediate environment, and their impact on the planet was negligible, existing as one species among many. The appearance of Homo erectus around 1.9 million years ago represented another major leap. Homo erectus was the first hominid to migrate out of Africa, spreading across Asia, and eventually into parts of Europe. This species was taller, more robust, and had a significantly larger brain than Homo habilis. They developed more sophisticated tools known as Acheulean hand axes, versatile implements for cutting, chopping and scraping. Crucially, Homo erectus mastered the control of fire. Fire provided warmth protection from predators and the ability to cook food, which made it more digestible and unlocked greater nutritional value, contributing to further brain development. The control of fire was a foundational technological advancement, allowing for a degree of environmental manipulation. Despite these innovations, Homo erectus lived as nomadic hunter-gatherers. Their impact on the planet was still minimal, and their settlements were temporary, leaving little behind but scattered stone tools and occasional fire pits. Their technology remained relatively static for over 1 million years, indicating a very slow pace of innovation compared to later human history. Archaic Homo sapiens, including Neanderthals and Denisovans, emerged roughly 600,000 to 400,000 years ago. These groups had even larger brains approaching modern human size and exhibited more complex behaviors, Neanderthals, for instance, were skilled hunters using Mousterian tools, which involved more refined flaking techniques. They adapted to harsh Ice Age environments, lived in shelters, often caves, and showed signs of caring for the sick and elderly. There is evidence of symbolic thought in some archaic human populations, perhaps through simple adornments or burials. However, their populations remained relatively small and dispersed. There is evidence of symbolic thought in some archaic human populations, perhaps through simple adornments or burials. However, their populations remained relatively small and dispersed. Their technology, though advanced for its time, was still stone-based, and their societal structures were likely small-scale tribal groups. Their environmental impact was localized and temporary. The pivotal moment in the human timeline was the emergence of anatomically modern Homo sapiens in Africa approximately 300,000 to 200,000 years ago. These early modern humans possessed a cranial capacity and skeletal structure almost identical to people living today. The exact timing and spread are subjects of ongoing scientific debate, but the consensus is that our species originated in Africa and gradually diversified. For tens of thousands of years, these early Homo sapiens continued a hunter-gatherer lifestyle, slowly refining their tools and adapting to diverse African environments. The true acceleration of human technological and cultural development began with the global dispersal of Homo sapiens out of Africa. Starting perhaps 70,000 to 60,000 years ago, waves of modern humans migrated across the continents, eventually populating Asia, Europe, Australia, and finally the Americas. This process of global colonization was remarkable, demonstrating our species' incredible adaptability, resilience, and ingenuity. Along the way, Homo sapiens encountered and sometimes interbred with existing archaic human populations like Neanderthals and Denisovans. The period known as the Upper Paleolithic, roughly 50,000 to 10,000 years ago, witnessed a profound cultural revolution. This was not a biological change, but a shift in behavior and cognition. Homo sapiens developed highly specialized stone tools made from blades, bone tools, needles, and fishing hooks. Innovations included atlatls for throwing spears, bows and arrows, greatly improving hunting efficiency. But more significantly, this era saw the widespread emergence of symbolic thought and complex cultural practices. Cave paintings in places like Lascaux and Chauvet, elaborate carving sculptures and personal adornments indicate abstract thinking ritual and the transmission of complex ideas. These were not just survival tools, but expressions of a rich inner world and sophisticated social structures. Small bands of hunter-gatherers lived in temporary camps, but their artistic output suggests an increasing sense of community and shared narrative. Even during this period, however, human populations remained relatively small, and their environmental impact was still minor in the grand geological scheme, though some hypothesize their hunting practices may have contributed to the extinction of megafauna. The end of the last ice age, around 12,000 to 10,000 years ago, brought about significant environmental shifts. As glaciers retreated and global temperatures rose, new landscapes emerged, and existing ecosystems changed dramatically. This period of rapid environmental change set the stage for one of the most transformative events in human history, the Neolithic Revolution. The Neolithic Revolution, beginning roughly 10,000 years ago, was not a single event, but a gradual process that occurred independently in several regions around the world. It marked the transition from a nomadic hunter-gatherer lifestyle to a settled agricultural existence. Humans began to domesticate plants like wheat, barley, rice, and maize, and animals like goats, sheep, cattle, and pigs. This fundamental shift had profound consequences. Agriculture provided a more reliable food source, allowing for increased population densities. People began to live in permanent settlements, villages, and eventually towns. The need to manage crops and herds led to innovations in irrigation, land management, and food storage. The settled lifestyle also allowed for greater accumulation of possessions and the development of more complex social structures, including specialization of labor beyond food production. Potters, weavers, and builders emerged. Social hierarchies became more pronounced with leaders, priests, and warriors. The earliest cities like Çatalhöyük in modern-day Turkey demonstrate this transition with dense populations and interconnected dwellings indicating a high degree of social organization. This marked the first significant and sustained human impact on the landscape through land clearing for agriculture and the construction of permanent structures. Following the Neolithic revolution, the pace of human technological and societal development began to accelerate significantly. The Bronze Age, roughly 5,000 years ago, saw the discovery and widespread use of metallurgy. The ability to smelt copper and tin to create bronze, a harder, more durable metal, revolutionized tool-making, weapon production and art. This required specialized knowledge, mining, smelting and casting, which further drove labor specialization and trade networks. The Iron Age, following around 3,200 years ago, brought even harder and more abundant iron into use. These metallurgical advancements provided the foundation for more efficient agriculture, stronger military equipment and more durable construction tools. With agricultural surplus and advanced metallurgy, early states and empires began to emerge. These were larger, more complex political entities, often with centralized governments, legal systems and organized militaries. The first writing systems developed independently in Mesopotamia, Egypt, China and Mesoamerica, around 5,000 years ago. Writing was a revolutionary technology, allowing for the accurate recording of laws, historical events, religious texts, and economic transactions. This enabled the management of larger populations and more complex societies, and facilitated the transmission of knowledge across vast distances and generations. Monumental architecture such as the pyramids of Egypt or the ziggurats of Mesopotamia served as symbols of power and religious devotion, demonstrating the collective organizational capacity of these early civilizations. These structures left a significant, albeit localized, footprint on the landscape. The classical civilizations of Greece, Rome, China and India, flourishing from roughly 2,500 years ago onwards, represented peaks of early human achievement. They made immense contributions to philosophy, science, mathematics, law, engineering, art and literature. The Roman Empire, for instance, built vast networks of roads, aqueducts and cities, integrating diverse regions under a single political system. Chinese empires developed sophisticated bureaucracies and technological innovations like paper and gunpowder. Indian civilizations made advancements in mathematics and medicine. These civilizations demonstrated an unprecedented ability to organize vast populations, manage resources and project power across large geographic areas. Their environmental impact, while not global, was substantial within their regional spheres, including large-scale deforestation and mining. The period following the classical era, often referred to as the Middle Ages in Europe, or the continued flourishing of empires in Asia, saw a gradual accumulation of knowledge and a slow but steady pace of innovation. The Renaissance in Europe, starting around the 14th century, brought a renewed interest in classical learning and art. This was followed by the scientific revolution in the 16th and 17th centuries, which fundamentally changed humanity's understanding of the natural world through empirical observation and systematic experimentation. Figures like Copernicus, Galileo, and Newton laid the groundwork for modern science. These intellectual leaps paved the way for the dramatic changes that were to follow. The most recent and profound transformation in the human timeline was the Industrial Revolution beginning in the late 18th century. This period marked an unprecedented acceleration of technological advancement and societal change. The invention of the steam engine harnessed new forms of energy from fossil fuels, enabling factories to operate on a massive scale. This led to mass production urbanization as people moved to cities for work and dramatic changes in social structures. New materials like steel and new technologies like railways and telegraphs revolutionized transportation and communication. The Industrial Revolution marked the point where human activity began to have a global and increasingly pervasive impact on the planet. The burning of fossil fuels began to alter atmospheric composition, leading to climate change. Large-scale mining and manufacturing created widespread pollution and altered landscapes on a scale previously unimaginable. This was the true dawn of a technologically advanced civilization with a planetary footprint. The 20th and 21st centuries have seen this acceleration continue at an exponential rate. The development of electricity, the internal combustion engine and flight further transformed daily life and global connectivity. The mid-20th century brought the atomic age with nuclear power and weapons, demonstrating humanity's capacity for both immense creation and destruction. The late 20th century ushered in the information age, driven by digital technology, computing and the internet. This era has created a globally interconnected society where information can be transmitted instantly, and knowledge accumulates at an ever-increasing pace. Space exploration has extended humanity's reach beyond Earth. Genetic engineering and artificial intelligence are pushing the boundaries of what is possible. When we look at the entire human timeline, it is striking how recently the characteristics of an advanced civilization with a global footprint have emerged. For millions of years, hominids lived as small groups with localized and transient impacts on their environment. The shift to agriculture is only about 10,000 years old. The invention of writing is about 5,000 years old. The Industrial Revolution, which began to leave a truly global and chemically detectable signature, is barely 250 years old. The digital age is only a few decades old. This means that the period during which human civilization has been capable of leaving the kind of long-lasting geological signatures that might be detectable millions of years later is incredibly brief, perhaps only a few hundred years. This short span of significant impact compared to the immense backdrop of Earth's geological history highlights the challenge of finding similar traces from any hypothetical prior civilization. Our timeline serves as a stark comparison, a demonstration that even highly intelligent life can exist for vast periods without leaving a detectable industrial signature, and that a profound planetary impact is a very recent and specific phase of development. The question of whether advanced civilizations existed on Earth millions of years before humans is a fascinating and deeply thought-provoking inquiry, a blend of scientific speculation and profound philosophical considerations. It moves beyond the realm of pure science fiction and into the territory of what some scientists call speculative science, a thought experiment that can help us refine our understanding of Earth's deep history and the limits of scientific detection. At the heart of this question lies a concept popularized by two prominent scientists, Adam Frank, an astrophysicist, and Gavin Schmidt, a climate scientist and director of the NASA Goddard Institute for Space Studies. They formally introduced and explored this notion, naming it the Silurian hypothesis. The name Silurian hypothesis itself carries a playful nod to popular culture, specifically a reference to the classic British science fiction television show Doctor Who. In one storyline, the Doctor encounters an ancient reptilian race known as the Silurians, who are an intelligent civilization that existed on Earth millions of years ago, long before the rise of humanity. While the science fiction version is fantastical and not scientifically rigorous, the choice of name by Frank and Schmidt acknowledges the speculative nature of their inquiry while grounding it in scientific principles. They were not suggesting that actual reptilian humanoids once walked the Earth, but rather using the idea as a springboard for a serious scientific thought experiment. The core premise of the Silurian hypothesis is simple yet profound. Could an industrial civilization similar to or even more advanced than our own have existed on Earth millions of years in the past and left behind detectable geological traces? The key term here is industrial, because such a civilization would necessarily manipulate vast amounts of energy and resources, leaving a measurable footprint on the planet's chemistry and geology. This distinguishes it from previous questions about alien life, which often focus on extraterrestrial beings. Here the question is about intelligent life that developed on our own planet, but at a time when humans were not even a distant biological possibility. Frank and Schmidt's work arose from a broader discussion about searching for technosignatures on exoplanets, distant worlds orbiting other stars. When astronomers search for signs of alien life, they often look for biosignatures like oxygen in an atmosphere which indicates biological activity. But they also consider technosignatures, which are signs of technology. The question then arose, if we are looking for technosignatures on other planets, what kind of technosignatures would our own human civilization leave behind that might be detectable by a future civilization or alien observers millions of years from now? And if we could imagine our own future fossil record, could we then look for similar patterns in Earth's deep past? This intellectual exercise inverted the typical search for alien life, turning the focus inward to our own planet's ancient history. The hypothesis is not about finding direct artifacts in the conventional sense. The immense timescales involved make the survival of recognizable buildings tools or even skeletal remains of an ancient civilization highly improbable, if not impossible. As explored in discussions about deep time, the Earth is a dynamic planet with powerful forces like plate tectonics, erosion, and metamorphism constantly recycling and transforming its crust. A city built 200 million years ago would likely have been completely subducted into the mantle or crushed and melted beyond recognition into metamorphic rock. Even durable materials would suffer immensely over such durations. Therefore, the Silurian hypothesis focuses on indirect geological signatures. What kind of large-scale and long-lasting effects could an industrial civilization have on its planet? Adam Frank and Gavin Schmidt propose looking for parallels with the Anthropocene, which is the unofficial geological epoch characterized by human activity's dominant impact on Earth's geology and ecosystems. Our current civilization is creating a detectable layer in the geological record, a distinct fingerprint that future geologists, if they exist, might identify millions of years from now. So what kinds of traces would an industrial civilization leave? They could include, first, chemical anomalies in the geological record. Our industrial civilization releases vast amounts of carbon dioxide from burning fossil fuels, altering the carbon cycle and leading to detectable shifts in carbon isotopes in sediments. A similar ancient civilization could have done the same. They might have released other persistent pollutants like unusual nitrogen compounds or altered oxygen levels in the atmosphere or oceans. Detecting these precise chemical shifts over millions of years would be extremely challenging, as natural processes also cause such fluctuations, but a distinct pattern or rapid onset could be indicative. Second, unusual mineral deposits. An industrial civilization would engage in a large-scale mining for metals and other resources. This could lead to concentrated deposits of certain minerals or elements that are unusual in natural geological formations. The systematic extraction of specific elements might also leave behind unusual depleted zones. Over vast timescales, these might be hard to distinguish from natural geological processes, but a highly anomalous concentration or distribution could raise questions. Third, technofossils. While direct artifacts are unlikely to survive, the concept of technofossils suggests that extremely durable and unique materials created by an advanced civilization might persist in some form. Think of plastics, which degrade slowly but leave microplastic particles. Perhaps an ancient civilization developed a super durable material that would leave microscopic but distinct chemical or structural traces in rock layers. Or perhaps massive large-scale construction projects such as global road networks or engineered landforms might leave geological patterns that are too geometric or systematic to be natural. However, these are highly speculative, and their detectability after millions of years is questionable. Fourth, altered biological evolution. While more indirect and harder to prove, an ancient civilization might have inadvertently or deliberately impacted the course of biological evolution. This could involve leading to the extinction of certain species, or conversely fostering the rapid diversification of others. However, disentangling such an impact from natural evolutionary processes and major extinction events would be a monumental task. The challenge of detecting these traces is immense. Earth's deep time processes are extraordinarily effective at erasing and transforming evidence. Subduction zones, where oceanic plates dive beneath continental plates, consume and recycle crust, along with anything built on it. Continental erosion by wind, water and ice constantly wears down mountains and landscapes, burying or exposing and destroying any surface features. Metamorphism, caused by intense heat and pressure deep within the Earth, can fundamentally change the composition and structure of rocks, obliterating any subtle chemical or physical signatures. Even within sedimentary layers where fossils are preserved, the process of fossilization is rare and highly selective, preserving only a tiny fraction of past life. The Silurian hypothesis essentially asks, what would the Anthropocene look like if it were a Paleocene? The Paleocene epoch, 66 to 56 million years ago, was a period of significant global warming known as the Paleocene-Eocene Thermal Maximum, or PTM. This event involved a rapid release of carbon into the atmosphere and oceans, leading to a spike in global temperatures. Scientists can detect this event in the geological record through characteristic changes in carbon isotopes and sedimentation patterns. The question then becomes, was the PTM a purely natural event, or could it have been influenced by an ancient industrial civilization? While the scientific consensus attributes PTM to natural volcanic activity or methane hydrate releases, Frank and Schmidt argue that the characteristics of such an event could in principle also be consistent with the signature of a massive carbon release from an ancient technological civilization. This does not mean they believe the PET was caused by a Silurian civilization, but rather that the methodology for distinguishing natural from artificial events in deep time is precisely what the hypothesis encourages us to develop. The scientific methodology for exploring the Silurian hypothesis is not about finding smoking gun evidence immediately, but about establishing a framework for investigation. It involves 1. Defining the potential types of detectable signatures, 2. Understanding the natural background rates and variations of these signatures in Earth's history, 3. Identifying anomalous patterns that deviate significantly from natural variations, 4. Developing robust methods to distinguish between natural and potentially artificial causes for these anomalies. This approach encourages scientists to look at existing geological data with a new perspective, asking unconventional questions and perhaps reinterpreting subtle patterns that were previously dismissed as noise or natural variation. The implications, if evidence of a pre-human civilization were found, would be profound for humanity. It would fundamentally alter our understanding of our place in the cosmos. We would no longer be seen as the unique and sole intelligent technological species to have arisen on Earth. It would challenge many of our philosophical and religious beliefs about human exceptionalism. It would force a re-evaluation of the entire history of life on Earth, and perhaps even prompt a reassessment of how we define progress and our own legacy. The implications for science would be immense, opening entirely new fields of study into ancient planetary engineering or biological manipulation. Conversely, if after extensive and rigorous investigation no such evidence is found, it would strengthen the hypothesis that human civilization is indeed unique on Earth, perhaps supporting various great filter theories that suggest major hurdles to the emergence or long-term survival of advanced technological life. It could imply that the conditions necessary for complex life to evolve and then achieve industrial capability are exceptionally rare, or that such civilizations are inherently short-lived, leaving no lasting signature. The Silurian hypothesis serves as a powerful thought experiment. It encourages humility and open-mindedness in science, reminding us that our understanding of Earth's past is constantly evolving. It is not about proving the existence of ancient aliens on Earth, but about using the framework of scientific inquiry to explore the very edges of possibility. By asking these questions, we gain a deeper appreciation for the immense geological forces that shape our planet, the fragility of any long-term record, and the perhaps fleeting nature of even the most advanced civilizations. It pushes the boundaries of conventional thinking about Earth's history and our own place within it. Investigating highly speculative questions like the possibility of advanced civilizations existing millions of years before, humans requires a robust and adaptable scientific methodology. While the topic might sound like science fiction, the approach remains rooted in the fundamental principles of scientific inquiry, emphasizing testable hypotheses, empirical evidence, and the crucial concept of falsifiability. Scientists approach such grand questions not by seeking definitive proof immediately, but by systematically exploring what could be known, how it could be known, and what evidence would definitively rule out a possibility. The scientific method at its core is a systematic way of gaining knowledge about the natural world. It begins with observation. Even for the distant past, observations come from the geological record fossils and chemical analyses. From these observations, scientists formulate questions and then propose a testable explanation or hypothesis. A hypothesis is not just a guess, it is a proposed explanation for a phenomenon that can be tested through further observation or experimentation. For instance, a hypothesis related to the Silurian idea might be, if an industrial civilization existed 100 million years ago, then we should find specific geochemical anomalies in the geological record from that period. The critical aspect of a scientific hypothesis is its testability. For ancient events, we cannot perform laboratory experiments in the traditional sense. Instead, testing involves making predictions based on the hypothesis, and then looking for evidence in the Earth's historical record that either supports or contradicts those predictions. If our hypothetical ancient civilization used fossil fuels for energy similar to our own, then a prediction might be that there would be a significant and unusual spike in certain carbon isotopes in sedimentary layers from that time. Scientists would then analyze rock core samples from that specific period to look for such a signature. Empirical evidence is the cornerstone of scientific inquiry. It refers to information gained by observation or experimentation. For the deep past, this evidence is almost always indirect. We cannot directly observe a dinosaur, much less an ancient factory. Instead, we rely on proxies and signatures preserved in the Earth's archives. Fossils are indirect evidence of past life. Sediment layers are indirect evidence of past environments and climates. Chemical signatures in rocks are indirect evidence of past atmospheric or oceanic conditions. The challenge for a pre-human civilization hypothesis is that its direct physical evidence, if it ever existed, would be overwhelmingly destroyed by geological processes over millions of years. Therefore, the search must focus exclusively on indirect signatures that are durable enough to persist. Falsifiability is a defining characteristic of a scientific hypothesis. A hypothesis must be capable of being proven wrong. If a hypothesis cannot be disproven, it falls outside the realm of science. For example, the hypothesis that invisible undetectable gnomes live in the centre of the Earth is not scientific, because there is no conceivable way to prove it false. In contrast, if we hypothesize that a pre-human civilization left a specific iridium layer in the geological record similar to the one found at the Cretaceous-Paleogene boundary, we can then test this by looking for iridium layers at the hypothesized time. If we search comprehensively and find no such layer, then the hypothesis is weakened or perhaps even falsified. Even if an iridium layer is found, it must then be rigorously investigated to rule out natural explanations such as an asteroid impact or volcanic activity. The scientific process demands that alternative explanations are considered and eliminated through evidence. When investigating a highly speculative question like ancient Earth civilizations, scientists adopt a multidisciplinary approach combining expertise from various fields. Geologists provide knowledge of rock formations, dating methods, and Earth processes over deep time. Paleontologists understand the fossil record and the evolution of life. Chemists analyze the elemental and isotopic composition of ancient rocks and sediments. Climate scientists model past atmospheric and oceanic conditions. Each discipline brings its unique tools and perspectives to bear on the problem, helping to build a comprehensive picture and identify potential anomalies. The search for evidence of an ancient civilization in the absence of direct proof relies heavily on examining indirect signatures. These signatures are subtle changes in the Earth's physical or chemical record that would be difficult to explain by natural processes alone. The logic here is by analogy with our own human civilization, the Anthropocene. We know that human industrial activity has produced a unique and measurable impact on the planet. Therefore, if a similar industrial civilization existed in the deep past, it might have left a comparable fingerprint. One of the primary areas of investigation for indirect signatures is geochemical anomalies. Our modern industrial civilization has profoundly altered the global carbon cycle through the burning of fossil fuels releasing vast amounts of carbon dioxide into the atmosphere. This CO2 has a distinct isotopic signature, different from naturally occurring carbon in the atmosphere or oceans. If an ancient civilization engaged in similar large-scale combustion, it might have left a corresponding spike in anomalous carbon isotopes in sedimentary layers or ancient soil horizons. Scientists would analyze the carbon isotope ratios in rock samples from various geological periods, looking for sharp, unusual increases that cannot be attributed to known natural events, like massive volcanic eruptions or methane hydrate releases. The challenge is that natural events also cause such shifts, and disentangling an artificial signal from a natural one requires meticulous analysis and multiple lines of evidence. Beyond carbon, other elements might serve as tracers. For example, large-scale industrial processes often involve the mining and refining of heavy metals like lead, copper, or zinc. Elevated concentrations of these elements in ancient sediments or ice cores might point to industrial activity. However, natural geological processes such as hydrothermal vents or certain types of ore deposits also concentrate these metals. The key would be to find concentrations that are unusually widespread, localized in a manner inconsistent with natural processes or accompanied by other corroborating evidence. Mineralogical signatures are another area of interest. An advanced civilization might create unique synthetic materials or alter natural minerals in ways that leave a lasting imprint. While highly improbable for very ancient periods, perhaps extremely durable artificial compounds or microplastic-like particles could be identified through advanced microscopy and chemical analysis of rock samples. Additionally, large-scale mining operations would create distinct geological formations like tailings ponds or altered ore bodies that might survive in a highly metamorphosed but still detectable form. The challenge is again distinguishing these from natural mineral formations or altered volcanic deposits. Stratigraphic anomalies refer to distinct layers or sequences of rock that deviate from expected natural patterns. For example, a widespread layer of highly processed waste material, or a layer with a unique combination of elements not typically found together, could indicate non-natural processes. However, the dynamic nature of Earth's crust means that such layers would likely be compressed, deformed, and metamorphosed beyond recognition over millions of years. Still, the search for sudden, geologically unexplainable shifts in rock composition remains a part of the inquiry. Isotopic anomalies extend beyond carbon. Industrial processes can alter the isotopic ratios of other elements like nitrogen or sulfur. For instance, the production of synthetic fertilizers could change nitrogen isotope ratios in ancient soils or sediments. Similarly, certain industrial processes can create unique sulfur isotope patterns. Identifying these subtle shifts in the context of deep time would require extremely precise analytical techniques and a thorough understanding of natural geochemical cycles to rule out confounding factors. Even structural geological features are considered, though with immense skepticism. Could incredibly large-scale and precise structures like a global transportation network or massive energy harvesting structures leave behind patterns that, if deeply buried and metamorphosed, might still show an unnatural geometry? This is highly speculative given the destructive power of plate tectonics and erosion, but as a thought experiment it forces scientists to consider the limits of what could possibly survive. The scientific inquiry into the Silurian hypothesis also emphasizes the null hypothesis. In science, the null hypothesis is the default position that there is no effect or no relationship between observed phenomena. In this context, the null hypothesis is that any observed geological or chemical patterns are the result of purely natural processes. The burden of proof lies with those proposing an alternative explanation, such as an ancient civilization. To overturn the null hypothesis requires compelling evidence that cannot be explained by any known natural phenomenon. This rigorous standard prevents premature conclusions based on limited or ambiguous data. Peer review and scientific consensus are vital steps in this process. Once researchers gather data and formulate their findings, they submit their work to scientific journals where it is scrutinized by other experts in the field. This peer review process ensures that the methodology is sound, the data is interpreted correctly, and the conclusions are supported by the evidence. Only after undergoing this rigorous vetting process and gaining acceptance from a broad scientific consensus does a hypothesis gain widespread credibility. This collaborative and critical process is essential for separating speculative ideas from scientifically robust theories. Despite the intriguing nature of the Silurian hypothesis, the limitations and challenges are immense. One of the biggest challenges is the signal-to-noise ratio. The Earth's geological record is overwhelmingly dominated by natural processes. Distinguishing a potentially faint artificial signal from the overwhelming noise of natural geological and environmental fluctuations is incredibly difficult. Natural events like massive volcanic eruptions, superplumes, or major asteroid impacts can leave very distinct and widespread chemical and geological signatures that might mimic some of the predicted industrial footprints. Preservation bias is another major hurdle. The geological record is incomplete and heavily biased. Only a tiny fraction of life that has ever existed is preserved as fossils. Soft-bodied organisms rarely fossilize. Similarly, ephemeral structures or materials that degrade quickly are lost forever. What survives over millions of years are typically the most durable materials or widespread chemical changes that become integrated into vast rock formations. This bias makes it extremely hard to find specific localized evidence. Ambiguity is also a persistent problem. Many geological features or chemical anomalies can have multiple natural explanations. For instance, a sudden spike in carbon isotopes could be due to massive volcanism or the melting of frozen methane hydrates in addition to hypothetical industrial emissions. Disentangling these causes requires a sophisticated understanding of Earth systems and a constellation of corroborating evidence. The lack of ground truth, where we cannot directly observe the past event, means that inferences are always based on interpreting indirect evidence through our understanding of modern processes. Despite these immense challenges, the value of speculative science like the Silurian hypothesis is considerable. Even if it is never definitively proven or is ultimately falsified, it pushes the boundaries of our understanding. It encourages scientists to look at existing geological data with fresh eyes, to refine methodologies for detecting subtle signals, and to consider what we truly know and do not know about Earth's deep history. It prompts important questions about the long-term environmental impact of our own civilization and what kind of legacy we're leaving for the far future. By grappling with such grand questions, we deepen our scientific toolkit and broaden our intellectual horizons. It fosters a healthy skepticism about what we assume to be true about the uniqueness of human technological development on this planet, and reminds us of the vastness of time and the dynamism of Earth. The Earth itself is an immense and dynamic archive, a colossal library of its own history recorded in layers of rock ice and sediment. Understanding the types of records preserved by Earth's geological and paleontological processes over vast stretches of time is essential for any attempt to reconstruct past environments, climates, and life forms. However, this archive is far from perfect. It is incomplete, fragmented, and constantly being rewritten by the very forces that create it. The immense scale of geological time means that only the most durable and widespread evidence has any chance of surviving for millions of years. The primary recorders of Earth's history are sedimentary rocks. These rocks form from the accumulation of sediments, which are particles derived from the weathering and erosion of older rocks, or from the remains of organisms or chemical precipitates. These sediments are transported by wind, water, or ice, and then deposited in layers known as strata. Over time, as more layers accumulate, the weight compacts the lower layers, and minerals precipitate from groundwater, cementing the particles together, a process called lithification, turning the sediment into solid rock. Different depositional environments produce different types of sedimentary rocks and features. Marine environments, for instance, are vast and diverse. Deep-sea sediments like abyssal clays and oozes composed of microscopic marine organisms accumulate very slowly, but can provide a continuous record over long periods, if not affected by subduction. Shallow marine environments like continental shelves are often characterized by sandstones, limestones and shales reflecting varied conditions from high-energy coasts to calmer, deeper waters. Lakes or lacustrine environments can preserve fine-grained sediments, often with annual laminations or varves reflecting seasonal changes, providing high-resolution climate data over thousands to hundreds of thousands of years. Rivers or fluvial environments deposit sands and gravels in channels and floodplains. Aeolian or wind-blown environments create vast sand dunes and loess deposits in deserts. Glacial environments leave behind unsorted sediments called till and distinct landforms. Each of these environments leaves unique clues about the past. The study of sedimentary rock layers and their arrangement is called stratigraphy. It is governed by several fundamental principles. The principle of superposition states that in an undisturbed sequence of sedimentary rocks, the oldest layers are at the bottom and the youngest are at the top. This provides a relative chronological order. The principle of original horizontality posits that sedimentary layers are originally deposited in flat horizontal layers. If we find them tilted or folded, we know that geological forces have acted upon them after deposition. The principle of lateral continuity suggests that sedimentary layers extend laterally in all directions, unless interrupted by a physical barrier. This helps correlate rock layers across different outcrops. The principle of faunal succession states that fossil organisms succeed one another in a definite and determinable order, which allows for the relative dating and correlation of rock strata across wide geographic areas. These principles allow geologists to piece together sequences of events even when rock layers are separated by vast distances. Within these sedimentary rocks, a wealth of information is preserved. The grain size and type of sediment tell us about the energy of the depositional environment and the proximity to the source of the sediment. For example, coarse gravels indicate high-energy river currents, while fine mudstones suggest calm, deep water. Sedimentary structures, such as ripple marks formed by currents, cross-bedding from migrating dunes or ripples and mud cracks, indicating subaerial exposure and drying, provide clues about the conditions during deposition, including the direction of ancient currents or the presence of ancient shorelines. Crucially, sedimentary rocks are the primary repository for fossils. Fossils are the preserved remains or traces of ancient life. The process of fossilization is relatively rare, requiring specific conditions like rapid burial to protect the remains from scavengers and decay, and often an oxygen-poor or anoxic environment. Hard parts like bones, teeth, shells, and wood are much more likely to fossilize than soft tissues. There is a significant bias in the fossil record. Organisms with hard parts that lived in environments conducive to rapid burial like shallow marine environments or swamps are overrepresented, while soft-bodied terrestrial organisms are very rarely preserved. Fossils provide invaluable information about past life forms, their evolution, anatomy, behavior, and the ecosystems they inhabited. They tell us about ancient biodiversity and the timing of major evolutionary events and extinctions. Trace fossils such as footprints, burrows, and coprolites, or fossilized feces provide direct evidence of animal behavior rather than just their physical form. Paleosols or ancient soils are another type of record found within sedimentary sequences. These are fossilized soil layers that preserve information about ancient terrestrial environments, climates, and vegetation. Their chemical composition and structure can indicate whether the past climate was arid, humid, or temperate, and what kind of plant life was present. The chemical composition of sedimentary rocks provides further insights. The presence and ratios of certain elements or isotopes can reveal details about past atmospheric conditions, ocean chemistry, and global biogeochemical cycles. For example, oxygen-isotope ratios in ancient marine shells can tell us about past ocean temperatures and global ice volumes. Carbon isotope ratios in organic matter or carbonates can indicate major shifts in the global carbon cycle, possibly related to large-scale volcanic activity, biological productivity, or even changes in atmospheric carbon dioxide levels. Sulfur isotopes can provide clues about ancient anoxic conditions in oceans. These chemical signatures can be extremely subtle and require highly precise analytical techniques to detect and interpret. Beyond sedimentary rocks, igneous and metamorphic rocks also contribute to Earth's record, but in different ways. Igneous rocks form from the cooling and solidification of molten rock called magma or lava. Extrusive igneous rocks like basalt form from lava, erupting onto the Earth's surface, cooling quickly, and forming fine-grained rocks. Intrusive igneous rocks like granite form when magma cools slowly beneath the Earth's surface, creating coarse-grained rocks. Igneous rocks are crucial for absolute dating using radiometric methods, as their minerals often contain radioactive isotopes that began decaying at the time of the rock's formation. They provide precise time markers in the geological record and reveal information about the Earth's interior processes and tectonic settings. However, they generally do not preserve fossils or direct evidence of surface environments. Metamorphic rocks form when existing rocks are transformed by intense heat pressure and chemically active fluids deep within the Earth's crust. This process can completely alter the original mineralogy, texture, and structure of the parent rock. During metamorphism, any original features like fossils or sedimentary structures are usually destroyed. Metamorphic rocks primarily record the tectonic history of a region, revealing information about ancient mountain building events, continental collisions and subduction zones where immense forces reshape the crust. They tell us about the pressures and temperatures that rocks experienced, reflecting deep crustal processes. Beyond rock records, other archives provide shorter but often higher resolution insights into Earth's more recent past. Ice cores extracted from glaciers and ice sheets in places like Antarctica and Greenland provide an unparalleled record of past climates and atmospheric composition, stretching back hundreds of thousands of years, but not millions. Snowfall accumulates annually, compacting into distinct layers of ice. Trapped within these layers are tiny air bubbles that preserve samples of the ancient atmosphere, allowing scientists to directly measure the past concentrations of greenhouse gases like carbon dioxide and methane. The isotopic composition of the water molecules in the ice itself provides a proxy for past temperatures. Layers of volcanic ash dust and other aerosols also trapped in the ice provide evidence of past volcanic eruptions and major environmental events. While ice cores offer invaluable data, They do not extend back millions of years because older ice sheets are typically compressed, thinned, or melted by geothermal heat. Tree rings, also known as dendrochronology, provide a very high-resolution record of climate and environmental conditions for the last few thousand years. The width and density of annual growth rings in trees are influenced by factors like temperature and precipitation. By matching patterns of ring widths from living trees to dead trees, scientists can construct continuous chronologies, extending back millennia. However, this record is extremely limited in time and geographic scope compared to the vastness of geological time. Speleothems or cave formations like stalagmites and stalactites can also preserve climate records. These grow slowly as mineral-rich water drips through caves, depositing layers of calcite. The chemical composition, especially oxygen isotopes within these layers, can provide information about past rainfall amounts and temperatures. These records typically cover hundreds of thousands of years. Ocean sediment cores obtained by drilling into the seafloor provide long continuous records of marine environments and global climate change. These cores contain layers of fine-grained sediment, plankton remains, and volcanic ash. Microfossils like foraminifera and radiolarians are abundant in these sediments. The species composition and isotopic ratios of their shells can reveal past ocean temperatures, salinity, and productivity. Layers of volcanic ash provide time markers. However, the maximum age of ocean floor sediments is limited by the process of plate tectonics, as oceanic crust is continuously recycled into the Earth's mantle at subduction zones. Thus, most ocean floor sediments are no older than about 200 million years. The challenges to preservation over deep time are immense and paramount to understanding why evidence of an ancient civilization would be exceedingly rare. Plate tectonics is perhaps the most destructive force. The constant movement of Earth's tectonic plates means that land masses shift, continents collide, and ocean basins open and close. Oceanic crust is continuously formed at mid-ocean ridges and subducted into the mantle at convergent plate boundaries. This process effectively erases any record of anything built on or deposited on oceanic crust after about 200 million years. Continental crust is more stable, but is still subject to immense forces. It can be uplifted, folded, faulted, and eroded, exposing deeply buried rocks or burying surface features under kilometers of new sediment. Any structures or artifacts would be subjected to crushing pressures and intense heat, possibly metamorphosing them into unrecognizable forms. Erosion and weathering are relentless forces that constantly wear down Earth's surface. Wind, water, ice, and chemical processes break down rocks and transport the resulting sediment. Over millions of years, entire mountain ranges can be leveled, and vast quantities of material can be removed and redeposited elsewhere. Any surface features, including cities or industrial complexes, would inevitably be obliterated by these processes, unless buried very rapidly, and then protected from further erosion. Metamorphism caused by heat pressure and chemically active fluids deep within the Earth can completely alter the original composition and structure of rocks. This transformation destroys primary features like fossil, sedimentary structures, and any subtle chemical or physical signatures of original materials. An ancient factory made of metal and concrete, if buried deep enough, would be reduced to a collection of highly altered minerals with no recognizable form. Biological decay is another factor. Most organic materials, including the bodies of organisms, wood textiles, and many types of plastic, will rapidly decompose after death or exposure to the elements. Only under very specific conditions, like rapid burial in an anoxic environment, is organic matter preserved for long periods, for instance in the formation of fossil fuels like coal and oil. These are themselves indirect records of vast amounts of ancient organic life, but they do not preserve detailed structural information. Diagenesis refers to the physical and chemical changes that sediments undergo after deposition, but before full metamorphism. These processes, including compaction cementation and recrystallization, can also obscure or destroy original features and even some chemical signatures within the sedimentary layers, making interpretation more challenging. Finally, the Earth's record is full of gaps known as unconformities. These represent periods of erosion or non-deposition where geological layers are missing. This means the record is not continuous, but rather a series of snapshots with often vast periods of time unrepresented in a particular location. This incompleteness further complicates the search for rare and subtle signals from an ancient civilization. Despite these immense challenges, scientists reconstruct past environments and climates by piecing together these fragmented records. They use multiple proxies, meaning they gather different types of evidence and look for consistency. For example, if oxygen isotope data from ice cores pollen, records from lake sediments, and fossil evidence from trees all indicate a past period of warmth, this provides strong corroboration. Computer modelling also plays a crucial role, simulating past climates based on geological and chemical data, allowing scientists to test hypotheses about Earth system dynamics. Paleogeographic maps are constantly updated, reconstructing ancient landmasses and ocean distributions based on tectonic evidence and fossil distributions. In the context of searching for a pre-human advanced civilization, the nature of the surviving record would be extremely subtle. Direct structural remnants are highly unlikely. Instead, the focus would be on broad persistent chemical or mineralogical anomalies in sedimentary layers, perhaps a unique isotopic signature of carbon or nitrogen, widespread unusual metal concentrations, or a layer of highly processed synthetic materials that have somehow resisted complete degradation. These would be very faint signals against a background of overwhelming natural processes. The Earth's archives are vast, but their deciphering requires extraordinary scientific rigor and an understanding of the immense transformative power of deep time. The fossil record, though an invaluable window into Earth's ancient past, is inherently limited and biased. It provides an incomplete and selective archive of life's history, preserving only a tiny fraction of the organisms that have ever existed. When we consider the possibility of advanced civilizations existing millions of years before humans, these limitations become even more pronounced. The processes that lead to fossilization are rare and specific, making it exceedingly unlikely for soft-bodied organisms, ephemeral structures, or intricate technological artifacts to survive the vast stretches of geological time in an identifiable manner. The rarity of fossilization itself is a primary constraint. For an organism to become a fossil, a series of very precise and uncommon conditions must be met. The most crucial of these is rapid burial. When an organism dies, its remains are immediately subject to decomposition by bacteria and fungi and destruction by scavengers. If the remains are not quickly covered by sediment such as mud, sand, or volcanic ash, they will simply decay and disappear. Rapid burial protects the remains from physical damage and biological breakdown, allowing the long-term preservation process to begin. This is why marine environments or floodplains are often rich in fossils, as they provide ideal conditions for quick sedimentation. In contrast, organisms that die on dry land or in environments with high oxygen levels are far less likely to be preserved. Another critical condition for fossilization is anoxia, or the absence of oxygen. Most decomposition is carried out by aerobic bacteria which require oxygen to thrive. In oxygen-poor environments such as deep lake beds, stagnant swamps, or certain marine environments, decomposition is significantly slowed or halted. This allows soft tissues to persist long enough for mineralization to occur. Without anoxia, even rapid burial might not be enough to prevent decay, especially for soft-bodied creatures. Beyond rapid burial and anoxia, the process of mineralization is key. Over time, as the buried remains are subjected to pressure and chemical changes, minerals from groundwater can infiltrate the pores of bones or wood, replacing the organic material cell by cell. This process, known as permineralization, can create a stone replica of the original structure. In other cases, the original organic material may dissolve entirely, leaving an empty space called a mold, which can then be filled by new minerals forming a cast. Sometimes the organic matter is completely replaced by minerals in a process called replacement. The type of mineralization depends on the specific chemical conditions of the sediment and groundwater. The bias towards hard parts is perhaps the most significant limitation of the fossil record. Organisms with robust skeletal elements such as bones, teeth, shells, and woody stems are vastly more likely to be preserved than those composed primarily of soft tissues. These hard parts are naturally more resistant to decay and can maintain their structure long enough for the mineralization process to take place. The mineral components of bone and shell, for example, are already inorganic, making them more stable than purely organic matter. This explains why the fossil record is dominated by creatures with skeletons like vertebrates or shelled invertebrates, while the vast majority of soft-bodied life forms are missing from the record. Consider the immense diversity of life on Earth today. Soft-bodied organisms like worms, jellyfish slugs, or many types of insects far outnumber creatures with hard skeletons, yet their fossil record is incredibly sparse. Even for creatures with hard parts like dinosaurs, we rarely find complete skeletons. Most fossil discoveries consist of isolated bones or teeth. The chances of finding a complete well-articulated skeleton are very low. There are rare instances of exceptional fossil preservation sites known as Lagerstätten, which provide unique glimpses into ecosystems where soft-bodied organisms were preserved. The Burgess Shale in Canada is a prime example dating back to the Cambrian period over 500 million years ago. Its fine-grained sediments and anoxic conditions allowed for the preservation of many soft-bodied marine creatures, revealing a much richer and more diverse ecosystem than would be apparent from hard-part fossils alone. However, these sites are extremely rare across geological time. They are anomalies, not the norm. Even in these exceptional cases, the preservation often involves flattened and compressed impressions of the original soft tissues, not three-dimensional replicas. Beyond the physical remains of organisms, ephemeral structures pose an even greater challenge. Nests, temporary shelters, webs, burrows, and other constructions made by animals are generally not preserved in a meaningful way. While trace fossils like footprints or burrows can provide indirect evidence of animal activity, they are not the fossilization of the structure itself. A bird's nest or a beaver's dam would quickly disintegrate, leaving no lasting mark. These structures are built from organic materials or loosely bound sediments and are easily destroyed by weather decomposition or subsequent geological processes. Now we must apply these limitations to the search for intricate technological artifacts from a hypothetical pre-human civilization. The unlikelihood of their fossilization in an identifiable manner over millions of years becomes overwhelmingly clear. First, consider the complexity versus simplicity of artifacts. Simple tools made of very durable natural materials like stone axes from early human ancestors have a high chance of surviving. Stone is inert, does not decay, and can resist weathering for long periods. However, such simple tools lack the intricate detail necessary to identify them as products of an advanced technological society without context. Complex electronics, delicate machinery, or advanced composite materials that are characteristic of an advanced civilization would shatter, corrode, or degrade rapidly. Their delicate internal structures would be destroyed by the very processes that might lead to burial. Let us examine the materials used in modern advanced technology and their likely fate over deep time. Organic materials like wood textiles or most plastics and composites are highly susceptible to decay. Wood rots away, fabrics biodegrade. While some plastics are very slow to degrade, they do eventually break down under exposure to ultraviolet light oxidation and microbial action. Even if buried, they would likely transform into something unrecognizable, or simply leave behind a dispersed chemical signature rather than an intact artifact. The microplastics that are now pervasive in our environment might leave a thin layer in sediments, but these would be microscopic particles, not identifiable artifacts. Metals, which are crucial to industrial civilizations, would fare little better. Most common metals like iron, copper, and aluminum are highly reactive and prone to corrosion and oxidation when exposed to water or air. Iron rusts away, forming iron oxides that are indistinguishable from naturally occurring minerals after millions of years. Aluminum quickly forms a stable oxide layer, but over vast timescales, even this would degrade, and its metallic form would vanish. Even noble metals like gold and platinum, while highly resistant to corrosion, are rare and usually used in small quantities. A large metal structure like a skyscraper or a bridge would turn into a diffused scattering of metal oxides and other mineral components, indistinguishable from natural geological deposits. The sheer volume of material would be subject to chemical alteration and dispersal. Ceramics and glass are more durable than metals or organic materials. They are resistant to decay and many chemical reactions. However, they are brittle. A ceramic or glass object subjected to the immense pressures and tectonic forces within the Earth's crust over millions of years would almost certainly shatter into unidentifiable fragments. Furthermore, under conditions of increasing heat and pressure, these fragments could undergo metamorphism, recrystallizing into new minerals, losing all original structure and becoming indistinguishable from natural rock components. Think of a shard of glass turning into a quartz crystal. Concrete, a ubiquitous building material of our age, is a complex composite. While it is durable over human timescales, it is still susceptible to chemical degradation, weathering and physical breakdown. Over millions of years, concrete would gradually remineralize, becoming chemically and structurally indistinguishable from natural rock components. The aggregate within the concrete would be released and the cement matrix would transform. The distinctive chemical signature of concrete might persist as a diffused presence in geological layers, but not as a recognizable structure. The scale of impact versus artifact preservation is a crucial distinction. While an industrial civilization might leave a detectable global chemical signature in the Earth's strata that is very different from the survival of individual artifacts, the widespread alteration of geochemical cycles or the deposition of distinct layers of modified rock reflect cumulative processes over time and are thus more likely to persist as indirect evidence. These are signals, not physical objects. A single building or even a large city would be a mere speck on the planet's surface, easily obliterated by geological forces. Consider the analogy of ancient human artifacts. Stone tools made by early hominids millions of years ago have survived because stone is exceptionally durable and inert. However, artifacts made of wood or other organic materials from even a few thousand years ago are incredibly rare, requiring exceptional preservation conditions like burial in bogs or deserts. Even the impressive concrete structures of the Roman Empire dating back only a couple of thousand years are showing significant signs of degradation. Projecting this forward over tens or hundreds of millions of years, the chances of any intricate technological item surviving in a recognizable form approach zero. The needle in the haystack problem further compounds the limitations. Even if by some extraordinary chance an intricate technological artifact somehow survived the ravages of deep time, and geological processes finding it would be astronomically difficult. The Earth's crust is vast. Only a tiny fraction of its volume has been explored. The continuous recycling of crustal material means that most ancient rocks are either buried deep beneath the surface or have been subducted and destroyed. The sheer improbability of stumbling upon such an object makes its existence virtually untestable through direct discovery. In essence, the fossil record is an amazing but highly biased and incomplete window into the past. It primarily preserves hard parts of organisms that lived in specific environments conducive to rapid burial and anoxia. It struggles to preserve soft-bodied creatures or ephemeral structures. For intricate technological artifacts made of materials that corrode, degrade, or shatter, under geological forces, the limitations of the fossil record are overwhelming. While an ancient civilization might leave broad, persistent chemical or geological signatures on a planetary scale, the survival of identifiable technological objects over millions of years is practically impossible, given our understanding of Earth's dynamic processes. The record primarily preserves the broad brushstrokes of life's evolution, not the fine details of lost civilizations. When contemplating the possibility of an ancient industrial civilization existing millions of years before humans, the search for evidence shifts from direct artifacts to indirect geological signatures. These are broad, pervasive, and chemically stable changes in the Earth's rock and sediment layers that could potentially reveal a past planetary scale technological impact. The focus is on widespread anomalies in geochemical cycles, unusual isotopic ratios, or distinct layers of modified rock that cannot be readily explained by natural geological phenomena. The best analogue for understanding these potential ancient signatures is our own human civilization's impact on Earth, a period often referred to as the Anthropocene. Human activities are fundamentally altering Earth's systems at a geological scale, creating a distinctive and measurable fingerprint in the planet's stratigraphy that future geologists, millions of years from now, might discern. By examining our own indelible mark, we can conceptualize what a prior advanced civilization might have left behind. One of the most profound human impacts is on the global carbon cycle. The widespread burning of fossil fuels like coal oil and natural gas has released immense quantities of carbon dioxide into the atmosphere, leading to a rapid increase in atmospheric carbon dioxide concentrations. This carbon dioxide has a distinct isotopic signature. Fossil fuels are derived from ancient organic matter, which preferentially incorporates lighter carbon, 12 isotopes over heavier carbon, 13 isotopes. When these fuels are burned, they release carbon-12 into the atmosphere, causing a measurable decrease in the carbon-13 to carbon-12 ratio in the atmosphere, oceans, and sedimentary organic matter. This phenomenon, known as the Suez effect, is a clear anthropogenic signal. If an ancient industrial civilization similarly relied on fossil fuels or other large-scale combustion processes, a similar rapid and pronounced negative carbon isotope excursion might be detectable in geological strata from that period. Beyond carbon, human activities have altered other major biogeochemical cycles. The nitrogen cycle has been profoundly impacted by the industrial-scale production of synthetic nitrogen fertilizers using the Haber-Bosch process. This has dramatically increased the amount of reactive nitrogen in the environment, leading to altered nitrogen isotopic ratios in soils and sediments. Similarly, human mining and agricultural practices have redistributed phosphorus on a global scale. An ancient civilization engaging in similar activities would leave comparable isotopic or elemental anomalies in these critical nutrient cycles. Our current human footprint also includes unique stratigraphic markers. The global dispersal of plastics, especially microplastics, is creating a new geological layer that will persist for millions of years. Plastics are synthetic polymers, largely resistant to natural degradation, and their ubiquitous presence in marine and terrestrial sediments will form a distinct marker. Concrete, a novel material developed by humans on a massive scale, has a unique chemical composition and structure that could theoretically be detectable as a modified rock type. Fly ash particles produced from coal burning are globally dispersed and have a distinct morphology and chemical signature. Furthermore, the mid-20th century saw a spike in radioactive isotopes from nuclear weapons testing, leaving a clear and distinct signal in sediments and ice cores globally. These novel materials and specific elemental or isotopic spikes represent specific geological signatures of our industrial age. A biological impact, the so-called Sixth Great Extinction Event, is another potential signature. Human activities like habitat destruction, pollution, climate change, and overexploitation are driving species to extinction at an unprecedented rate. If an ancient civilization caused a similar mass extinction, it might be identifiable by a sudden and widespread loss of biodiversity in the fossil record, combined with anomalous geochemical or mineralogical indicators. The homogenization of species through globalized agriculture and transport also creates a unique biological signal. Finally, human land use has significantly increased erosion and sediment transport rates, altering landscapes and leading to increased sediment delivery to rivers and oceans. This can result in changes in sedimentation patterns and sediment composition in geological records. Applying this analogue to deep time, the central question becomes what specific detectable signatures could a pre-human industrial civilization have left behind that would endure for millions of years? First, altered geochemical cycles would be key. A significant and widespread carbon isotope anomaly, distinct from natural fluctuations, would be a primary target. Scientists would look for a rapid negative or positive carbon isotope excursion, not easily explained by known natural events like massive volcanic eruptions or methane hydrate releases. The pace and scale of such a shift would be crucial. Similarly, large-scale manipulation of Earth's climate or energy use could potentially leave an oxygen isotope anomaly in ancient sediments, reflecting temperature changes. Industrial processes involving smelting or other chemical transformations could also alter sulfur isotope ratios. Large-scale ancient agriculture or industrial nitrogen fixation could lead to anomalous nitrogen isotope patterns in ancient soils or marine sediments. Second, unusual isotopic ratios of other elements could serve as tracers. For example, widespread smelting or industrial use of lead could leave a distinct lead isotopic fingerprint in ancient sediments. The systematic extraction and use of rare earth elements in high technology could result in unusual patterns of these elements in rock formations. Even anomalous concentrations or isotopic ratios of noble gases like helium or neon, which are generally inert, could be indicative of specific industrial processes or energy generation methods used by an ancient civilization. Third, distinct layers of modified rock or sediment might persist. This could include artificial mineral layers such as layers with mineral assemblages that are thermodynamically unlikely to form naturally, but are characteristic industrial byproducts. An example might be slag-like material from ancient smelting operations that has undergone metamorphism but still retains a unique chemical signature or crystalline structure. Layers with unusually high concentrations of specific elements beyond natural background levels, particularly those linked to widespread industrial processing or waste disposal, would also be targets. The most speculative idea is the survival of extremely durable synthetic materials, perhaps stable polymer structures or nanostructures that could resist degradation and be fossilized as microscopic patterns within rock formations. Fourth, a long-term climate perturbation could serve as a major signature. Could a pre-human industrial civilization have triggered a past warming or cooling event recorded in the geological record? The Paleocene-Eocene thermal maximum, or PETM, around 55 million years ago, is a rapid global warming event characterized by a significant negative carbon isotope excursion. While the current scientific consensus attributes the PTM to natural causes such as massive volcanic activity or the rapid release of methane clathrates, the characteristics of such an event could in principle also be consistent with the signature of a massive carbon release from an ancient technological civilization. The hypothesis does not claim the PETM was artificial, but uses it as an example of the kind of event that might be revisited with this new perspective. The challenge is in differentiating between such a natural event and a hypothetical artificial one based solely on the geological record. Fifth evidence of large-scale resource extraction could provide clues. Ancient widespread mining operations, even if their surface features eroded away, could leave deep scars in the crust. These could manifest as distinct geological structures, unusual distributions of rock types, or specific depletion of ore bodies in a widespread non-random pattern. While difficult to detect through current surface surveys, advanced seismic imaging or deep drilling might one day reveal such buried features. Finally, an ancient civilization could have caused an extinction event. While several mass extinction events are known in Earth's history, each typically attributed to natural causes like volcanism, asteroid impacts, or climate change, a civilization-caused extinction might have distinct characteristics such as the presence of specific pollutants in the extinction layer or a pattern of biodiversity loss that points to anthropogenic rather than natural drivers. Disentangling such a cause from the natural background would be extremely challenging. Differentiating these potential artificial signatures from natural phenomena is the central and most difficult challenge. Earth is a dynamic planet with powerful natural processes that can produce similar geological and chemical patterns. Massive volcanic eruptions, known as large igneous provinces for instance, can release enormous quantities of carbon dioxide and other gases into the atmosphere, leading to significant climate change and geochemical anomalies. Asteroid impacts leave distinct iridium layers and impact structures. Natural methane clathrate releases from the seafloor can cause rapid global warming. Ocean anoxic events, where vast stretches of the ocean become devoid of oxygen, lead to widespread black shale deposits and significant geochemical changes. Even natural mineral formation processes such as hydrothermal vents or evaporate deposits can create unusual concentrations of elements. To overcome this ambiguity, scientists require multiple lines of evidence. No single signature, no matter how striking, would be conclusive. A confluence of anomalies across different proxies, all pointing to an artificial origin, would be necessary. For example, an anomalous carbon isotope spike, accompanied by unusual metal concentrations, a sudden change in sedimentation patterns, and a mass extinction event, all occurring simultaneously and globally, might begin to build a more compelling case. The specificity and pattern of the signature are crucial. An artificial signature would need to exhibit a unique combination of characteristics, a temporal coherence and a global distribution that cannot be explained by any known natural Earth system process. It is about finding a signal that truly stands out from the overwhelming noise of natural geological activity. The scale of impact required for a geological signature to persist for millions of years means that the footprint must be planetary in scope and remarkably persistent. Localized anomalies, even if suggestive, could almost always be attributed to natural geological processes. The challenge of detection is also immense. Even if such signatures exist, finding them requires systematic global geological surveys and highly advanced analytical techniques. The vast majority of Earth's deep past record is either subducted recycled or hidden deep beneath the surface, making comprehensive investigation exceptionally difficult. The search for geological signatures of an ancient civilization is thus a quest for the faint echoes of a possibly profound past hidden within the deep and tumultuous archives of our planet. When considering the possibility of advanced civilizations existing millions of years before humans, the search for direct physical artifacts is largely a futile endeavour due to the destructive power of geological time. Instead, scientific inquiry shifts towards examining indirect evidence, specifically the industrial byproducts such a civilization might have left behind. These byproducts are the waste materials, chemical emissions, or altered mineral deposits that are a direct consequence of large-scale technological activity. Their potential persistence in the geological record offers a tantalizing, albeit challenging, proxy for past technological activity on a planetary scale. To understand what kinds of industrial byproducts might persist, it is instructive to look at our own human civilization's impact on Earth, a period increasingly referred to as the Anthropocene. Human industrial activity has fundamentally altered global biogeochemical cycles and introduced novel materials and chemical signatures into the planet's geological record. These serve as a powerful analogue for the types of detectable fingerprints an ancient industrial civilization might have left. One of the most significant byproducts of human industrial activity is the alteration of the global carbon cycle. The widespread burning of fossil fuels such as coal oil and natural gas releases vast quantities of carbon dioxide into the atmosphere. This carbon dioxide has a distinctive isotopic signature. Fossil fuels are derived from ancient organic matter that preferentially incorporates the lighter carbon-12 isotope over the heavier carbon-13 isotope during photosynthesis. When these fuels are combusted, this lighter carbon-12 is released into the atmosphere, leading to a measurable decrease in the ratio of carbon-13 to carbon-12 in atmospheric carbon dioxide, oceanic carbonates, and organic matter deposited in sediments. This phenomenon, known as the Suez effect, is a clear and pervasive anthropogenic signal. If a hypothetical ancient industrial civilization also relied on large-scale combustion of organic matter or other processes that preferentially released lighter carbon, a similar rapid and pronounced negative carbon isotope excursion could theoretically be detectable in geological strata from that period. The challenge lies in differentiating such a signal from natural carbon cycle variations caused by massive volcanic eruptions, methane hydrate releases from the seafloor, or major ocean anoxic events, all of which can also cause significant carbon isotopic shifts. The rapidity and scale of the change would be key discriminating factors. Beyond carbon, industrial processes involve the extraction, processing, and widespread use of various heavy metals. Mining and smelting activities concentrate metals like lead, mercury, cadmium, zinc, and copper in ways not typically found in natural geological settings or at such elevated levels. For example, historical records and ice core data show evidence of localized lead pollution from ancient Roman and Greek smelting activities. If an ancient industrial civilization operated on a global scale, we might expect to find elevated levels of these heavy metals dispersed widely in sediments, ice core analogues, or even ancient ocean floor deposits. The persistence of these metals depends on their chemical form and their incorporation into stable mineral phases. Many heavy metals can become incorporated into clays or other stable mineral matrices, allowing them to persist over geological timescales. The key would be to find unusual concentrations or distributions that are widespread and cannot be explained by natural geological processes like hydrothermal vents or localized ore deposits. The introduction of synthetic compounds is another unique byproduct of advanced technology. Plastics, pharmaceuticals, and various industrial chemicals are examples of materials with unique molecular structures that are not found in nature. While most organic synthetic compounds are prone to degradation over time through exposure to ultraviolet light oxidation and microbial action, some are remarkably persistent. Even if they break down, their molecular fragments or unique elemental ratios might remain embedded in the geological record. For instance, the widespread proliferation of microplastics in our current environment means that future geologists may find a distinct layer of these tiny plastic particles in sediments globally. While an intact plastic artifact would not survive millions of years, The unique chemical signature or even microscopic remnants of highly stable synthetic compounds could potentially persist as anomalous organic residues in deep time. Persistent organic pollutants, or POPs, are another class of compounds designed to be stable, and some might leave traces. Industrial processes, particularly those involving nuclear technology or certain types of energy production, might also release noble gases with altered isotopic ratios or in unusual concentrations. Noble gases like xenon and krypton are chemically inert, meaning they do not readily react with other elements, making them highly stable traces. Nuclear fission processes, for example, produce specific isotopic compositions of noble gases that are distinct from natural background levels. While their presence would be extremely subtle and require highly sophisticated analytical techniques, detecting such anomalous noble gas signatures in ancient atmospheric samples or trapped in stable mineral matrices could provide compelling evidence. The nitrogen cycle, like the carbon cycle, has been profoundly perturbed by human industrial activity, particularly through the large-scale production of synthetic nitrogen fertilizers using the Haber-Bosch process. This process converts atmospheric nitrogen into reactive forms, significantly altering the natural nitrogen isotope ratios in the environment. If an ancient civilization engaged in similar large-scale agriculture or industrial nitrogen fixation, it could theoretically leave a corresponding nitrogen isotopic anomaly in ancient soils or marine sediments. Similarly, widespread mining of phosphate rock for fertilizers and industrial use could lead to altered distribution patterns of phosphorus in sedimentary records. Beyond chemical alterations, industrial processes can lead to the formation of unique mineral phases. Smelting operations, for example, produce slag, which is a glassy or crystalline byproduct with a distinct chemical composition and mineralogy, not found in naturally occurring rocks. These unique industrial minerals formed at high temperatures could potentially persist in the geological record. Even if subjected to metamorphism, they might retain a specific chemical or textural signature that distinguishes them from naturally formed minerals. The creation of concrete, a binder that transforms sand and gravel into a strong composite, introduces a material with a unique mineralogy and chemical signature. While concrete itself might degrade, its constituent minerals and their arrangement could potentially leave a subtle trace. Microscopic particles are another category of industrial byproduct that could persist. Fly ash, a byproduct of coal combustion, consists of spherical glass particles with a distinct chemical composition and morphology. These particles are globally dispersed by atmospheric currents and are durable enough to be preserved in sediments and ice cores. Similarly, other specific industrial dusts or microscopic waste particles might possess unique characteristics that allow them to be identified in geological layers. Finally, radioactive isotopes represent a very specific and unambiguous type of industrial byproduct, particularly those associated with nuclear fission. Nuclear weapons testing and nuclear power generation produce unique radioisotopes that are not naturally abundant, such as plutonium-239 or cesium-137. While these isotopes have specific half-lives and would decay over millions of years, their decay products or the initial spike in their presence could serve as a very clear marker of ancient nuclear activity. Our own nuclear weapons testing in the mid-20th century has created a distinct and detectable radioactive layer in global sediments. An ancient civilization engaging in nuclear activities would leave a similar, albeit decayed, signal. The detectability of these industrial byproducts in deep time hinges on several factors. Chemical stability is paramount. The byproduct must be in a form that is resistant to dissolution, degradation, and chemical alteration over vast timescales. Many elements become incorporated into stable mineral structures or are adsorbed onto clay particles, allowing them to persist. Widespread dispersal is also crucial. Byproducts that are globally dispersed by atmospheric or oceanic currents, rather than being localized, create a more pervasive and therefore more detectable signal. Their incorporation into vast sedimentary layers increases the chances of their preservation across geological epochs. While high pressure and temperature during metamorphism would alter these byproducts, some fundamental chemical or isotopic anomalies might persist, even if the original physical form is completely obliterated. The anomaly would be altered but still chemically anomalous. the most challenging aspect of identifying ancient industrial byproducts is differentiating them from natural phenomena. Earth's history is filled with natural events that can produce similar geological and chemical patterns. Large-scale volcanism, for instance, can release massive amounts of carbon dioxide and other gases into the atmosphere, leading to significant climate change and geochemical anomalies. Hydrothermal vents on the seafloor can create localized deposits of heavy metals. Natural organic matter decay can influence carbon isotopes. The key to differentiation lies in identifying unique distinguishing features. Industrial processes often cause rapid, sudden shifts compared to the slower, more gradual changes of many natural cycles. The scale and distribution of an industrial signature would likely be global and pervasive, unlike many localized natural events. Most importantly, specific isotopic ratios or unique element associations might be produced by technological processes that are not found in nature. For instance, the specific isotopic fingerprint of anthropogenic lead differs from natural lead sources. The presence of novel molecular structures, even in degraded form if they could survive, would be a strong indicator. The search for ancient industrial byproducts is a quest for anomalous chemical or mineralogical fingerprints that suggest an industrial rather than a purely natural past. It demands meticulous analysis and a deep understanding of Earth system processes to rule out confounding natural factors. The limitations include the overwhelming background noise of natural geological and biological processes, the dilution of signals over vast timescales, the subduction or erosion of older records, and the inherent ambiguity of interpreting subtle anomalies without direct verification. Despite these challenges, the study of industrial byproducts offers one of the most scientifically grounded avenues for investigating the extremely speculative question of pre-human civilizations. The durability of artificial structures over immense geological timescales is a central analytical challenge when considering the possibility of pre-human advanced civilizations. While modern human civilization is characterized by monumental constructions from towering skyscrapers to vast road networks and subterranean installations, the relentless forces of Earth's natural processes make the long-term preservation of such structures over millions of years overwhelmingly unlikely. The planet's dynamism ensures that even the most robust human creations are ephemeral on geological scales, destined to be eroded, buried, or fundamentally transformed. Artificial structures are purpose-built, creations designed for specific functions by intelligent agents, differentiating them from naturally occurring formations. They are constructed from a wide range of materials, from natural ones like stone and wood to highly processed or synthetic ones such as concrete, steel, and plastics. Their scale varies from individual dwellings to immense cities and continent-spanning infrastructure projects. The immediate environmental degradation of abandoned artificial structures begins swiftly. Weathering processes involving wind, rain, ice, and fluctuating temperatures physically break down materials. Rain can dissolve certain rock types, wind can abrade surfaces, and the freeze-thaw cycle can crack concrete and stone. Erosion by water, wind, and even glacial ice continually transport material away, gradually dismantling and obliterating structures. Biological overgrowth is another immediate factor. Plant roots can penetrate and fracture foundations, while animals can inhabit and destabilize buildings. Rapid destructive events like fires, floods, and earthquakes can quickly reduce complex structures to rubble. Within mere centuries or a few millennia, most surface structures would be reduced to mounds of debris or reabsorbed into the landscape. Over millions of years, the degradation of the materials themselves is profound. Organic materials like wood textiles and many modern plastics and composites are highly susceptible to decay. Wood and other cellulose-based materials are readily consumed by microbes, insects, and fungi. Even if buried rapidly and deprived of oxygen, organic matter typically transforms through diagenesis into amorphous carbonaceous material, eventually forming coal or oil, completely losing its original structural identity. While microplastic fragments might persist, their macroscopic structural integrity would vanish. Metals, though seemingly durable, are highly reactive and subject to corrosion and oxidation. Iron and steel, the backbone of modern construction, will rust away when exposed to air and moisture, forming various iron oxides such as hematite and goethite, which are common natural minerals. A steel-framed skyscraper, over millions of years, would dissolve into a dispersed layer of iron-rich minerals indistinguishable from natural deposits. Copper oxidizes to form green or blue compounds. Aluminum forms a stable oxide layer, but over vast timescales even this protective layer will degrade, and the metallic aluminum itself will revert to its naturally occurring oxide forms. Even noble metals like gold and platinum, while highly resistant to corrosion, are rare and used in very small quantities in construction, thus offering little large-scale structural preservation. A large metal structure would not persist as a coherent form. Its material would be chemically altered and dispersed. Concrete, a material ubiquitous in human infrastructure, presents a fascinating case. While remarkably durable over human timescales, it is not impervious to the geological march of time. Concrete is susceptible to chemical weathering processes such as carbonation, where atmospheric carbon dioxide reacts with the cement paste, sulfate attack where sulfates in groundwater react with cement components, and alkali-silica reaction, where reactive silica in aggregates reacts with alkalis in the cement. Physical weathering agents like freeze-thaw cycles and abrasion also contribute to its breakdown. More critically, over millions of years, under immense pressure from overlying sediments and exposure to elevated geothermal temperatures, the distinct chemical bonds and mineral phases within concrete would undergo significant diagenetic or metamorphic alteration. The cement paste would recrystallize, and the aggregates would fuse or transform. The overall result would be a material chemically and structurally increasingly indistinguishable from natural sedimentary or low-grade metamorphic rock. Its unique man-made characteristics would be obliterated. Ceramics and glass, while resistant to biological decay and many chemical reactions, are brittle. An ancient ceramic pot or glass pane, if buried, would shatter into countless fragments under the immense pressures exerted by overlying sediments and tectonic forces. Furthermore, if subjected to the heat and pressure of metamorphism, these fragments would recrystallize into natural silicate minerals like quartz or feldspar, losing all original form and becoming indistinguishable from surrounding natural rock. Natural stone structures like the Egyptian pyramids or Roman aqueducts represent the most durable type of artificial construction. These are built from materials that are already naturally occurring rocks and are resistant to decay. However, their survival is also limited by geological processes. The specific type of stone matters greatly. Granite is highly durable, but limestone is susceptible to dissolution by acidic groundwater. Even solid rock mountains erode over millions of years. A surface structure, no matter how monumental, is constantly exposed to weathering and erosion. If not quickly buried, it would simply be worn away. If buried, it then faces the same challenges as other materials under pressure and heat. The impact of geological processes on structures goes beyond material degradation. Erosion, as already discussed, simply wears away anything on the surface. If a structure is not buried, it vanishes. However, rapid sedimentation and burial could theoretically protect structures from surface erosion. Imagine a city buried rapidly by a massive volcanic ash fall or catastrophic flood sediments. While protected from surface forces, it would then be subjected to immense overburden pressure from the accumulating layers above it. This pressure would compress to form and likely pulverize any intricate structures. Moreover, the geothermal gradient means that temperature increases with depth. Deeply buried structures would be subjected to temperatures that could cause phase changes and chemical reactions, further altering their materials. The processes of diagenesis and metamorphism would transform the original materials into new mineral assemblages, completely obliterating the original architecture. A buried city might become a localized zone of unusually textured rock, but not a recognizable city. Plate tectonics is the ultimate destroyer of ancient structures. The constant movement of Earth's tectonic plates ensures that most of the Earth's crust is continuously recycled. Oceanic crust is formed at mid-ocean ridges and then subducted back into the mantle at convergent plate boundaries. Any structures built on oceanic crust would be utterly consumed within a few 100 million years at most. Continental crust is more stable, but is still subjected to immense forces. Continental collisions lead to erogeny or mountain building where rocks are folded, faulted and thrust over one another. Any structure caught in such an event would be pulverized, stretched, or melted beyond recognition. Vast volcanic eruptions can bury regions under lava flows and ash, but these layers are then subject to erosion, or further burial and metamorphism. Given these overwhelming geological forces, what artificial structures could theoretically survive for millions of years in any discernible form? The answer is highly speculative and focuses on features far beyond individual buildings. Perhaps mega-engineering on a planetary scale involving massive subcrustal installations, deeply mined-out caverns, or extremely widespread deliberate alterations to the Earth's geomorphology might leave some highly altered and deeply embedded traces. Even these would be subject to metamorphism and tectonic forces, but their sheer scale and potentially anomalous geometry might persist as subtle geophysical anomalies. For example, through seismic imaging, highly altered zones of rock might show unnatural regular patterns or shapes at depth, hinting at a prior structured origin. Such detection would require extraordinary luck and future technological capabilities far beyond our current scope. Very large, deeply buried dumps of highly resistant industrial byproducts could also persist as distinct geological lenses, but these would be industrial byproducts more than structures. Consider the analogy of what would remain of a modern human city after 100 million years. It is highly probable that nothing recognizably structural would remain. The steel would have rusted, the concrete turned to rock, and organic materials vanished. What might endure would be a slight chemical anomaly in a sediment layer, or a localized patch of unusually altered and perhaps subtly textured rock that would be incredibly difficult to interpret as a former urban center. Even massive natural geological features like large impact craters, while globally significant, undergo significant erosion and infilling over millions of years, becoming less distinct over time. The challenges of detection for any such remnants are immense. The sheer scale of the search across the vastness of the Earth's crust is daunting. Distinguishing a highly altered and subtle artificial feature from the countless unusual but natural geological formations would be fraught with ambiguity. The interpretation of a highly metamorphosed lump of rock as a former building would be speculative at best, lacking definitive proof. In conclusion, the physical remnants of artificial structures are overwhelmingly unlikely to survive geological timescales in any recognizable form. Earth's dynamic processes are too powerful and relentless. The most one could hope for are highly altered, deeply buried geological anomalies that might hint at a prior structured origin, but their interpretation would be extremely challenging and deeply ambiguous. The concept of technofossils represents a frontier of speculative science, envisioning the hypothetical, extremely durable remnants of advanced technology that might persist through immense geological time, potentially offering a subtle clue to a pre-human civilization. Unlike biological fossils, which are the mineralized remains or traces of ancient life, technofossils would be the enduring signatures of artificial creations. The very idea pushes the boundaries of our understanding of material science, geological processes, and the limits of preservation over millions of years. It asks what pieces of technology, if any, could withstand the Earth's relentless forces of erosion, burial, pressure, and heat for epochs, emerging as recognizable, albeit highly degraded, traces of intelligence. To properly frame the concept of technofossils, it is helpful to draw an analogy with biological fossils. What allows a biological organism to fossilize? It requires exceptional conditions, rapid burial to protect remains from scavengers and decay, and often an anoxic or oxygen-free environment to prevent decomposition by microbes. Only a tiny fraction of all life that has ever existed has been preserved. Furthermore, there is a strong bias towards the preservation of hard parts such as bones, teeth, and shells, as these are inherently more resistant to decay and can be replaced by minerals. Soft-bodied organisms are exceedingly rare in the fossil record, only appearing in exceptional deposits where unique conditions allowed for their preservation. Now, apply this understanding to technology. Most human technology is inherently soft-bodied in a geological sense. It is made of materials that corrode, degrade, decompose, or are brittle and shatter under pressure. Our electronic devices, vehicles, textiles, and even many of our buildings are designed for human timescales of decades or centuries, not geological epochs. Therefore, for something to become a technofossil, it must possess extreme intrinsic material durability and resistance to geological forces, or be of a scale so vast that even its degraded remnants leave an anomalous pattern. The criteria for technofossil survival are extraordinarily demanding. First, the material itself must be exceptionally resistant to chemical corrosion, physical weathering, and biological degradation. This immediately rules out organic materials like wood, fabric, and most plastics which decay or break down. It also rules out common metals like iron and steel, which readily rust or corrode in the presence of water and oxygen. Ideal candidates would be highly stable synthetic compounds, certain types of ceramics or glassy materials, and perhaps exceptionally inert and dense metals that are not typically found in pure form in nature. Second, the technofossil must be able to resist immense geological forces. Once buried, it would be subjected to enormous pressure from overlying sediment, which can crush and deform objects. It would also experience elevated temperatures due to the Earth's geothermal gradient, potentially causing chemical reactions or phase changes within the material. Furthermore, tectonic activity can fold, fault, and metamorphose rock layers. A material that can survive metamorphism and still retain a unique property or structure would be truly extraordinary. This means that even if a material is durable on the surface, its persistence deep within the Earth's crust is a far greater challenge. Third, the material or structure must be inherently unique and recognizably artificial, distinct from anything that could form naturally. It should not have a natural analogue. This is crucial for distinguishing a technofossil from geological curiosities or highly altered natural formations. Its chemical composition, isotopic ratios, crystalline structure, or geometric pattern must unequivocally point to intelligent design and manufacturing. Let's consider some hypothetical technofossil materials or types that might meet these demanding criteria, while acknowledging the immense speculative nature of the concept. Ultra-durable synthetic polymers or composites might be one category. While most plastics degrade, it is conceivable that an advanced civilization could develop polymers designed for extreme longevity and resistance to environmental breakdown. Even if the macrostructure of a plastic object is lost, the unique molecular signatures or microscale patterns of such a superpolymer could potentially persist in rock, perhaps as a type of molecular fossil for technology. These would be exceedingly difficult to detect, likely requiring highly advanced analytical chemistry of ancient sediments. Engineered crystalline structures could be another avenue. Materials with precise atomic arrangements such as advanced ceramics or synthetic diamonds are incredibly hard and chemically stable. Large, highly pure single crystals of such materials, or materials with complex but precise lattice structures, might be resistant to some forms of degradation. However, they are still prone to fracturing under tectonic stress, and if buried deep enough, they could undergo recrystallization, losing their unique engineered structure and becoming indistinguishable from natural minerals. Exotic metals or alloys might also be considered. While common metals corrode, perhaps an ancient civilization developed alloys resistant to all known forms of chemical corrosion, or utilized metals not naturally found in pure form in Earth's crust in large quantities. The discovery of a large deposit of pure, non-native metal that persists might be an indicator. However, the rarity of pure native metals like gold or platinum suggests that even these are typically found in small veins or nuggets, not as bulk construction materials. Any large-scale use of metals implies extraction and refinement processes that are chemically unstable over deep time. The concept of self-assembling or self-repairing materials, often discussed in future technological visions, adds another layer of speculation. If an ancient civilization developed materials with these properties, how would their ultimate breakdown differ? Would they leave behind a more organized pattern of decay products, or a distinct trace of their designed functionality even after ceasing to operate? This is highly theoretical. Perhaps even more speculative is the idea of nanotechnology-derived structures. If an ancient civilization possessed advanced nanotechnology, could microscopic but highly ordered patterns or the components of nanomachines persist? These would be at the atomic or molecular level. While incredibly tiny, their precise non-natural arrangement might theoretically be detectable within a mineral matrix. However, the forces of degradation over millions of years, down to the atomic level, are immense, making this scenario almost impossible. Beyond small artifacts, technofossils could also encompass the remnants of massive planetary-scale engineering projects. These would not be individual buildings, but rather broad alterations to Earth's geology or deep crustal structures. For instance, massive deep geothermal installations designed to harness Earth's internal heat might leave distinct deep crustal signatures in rock density, thermal anomalies, or unusual mineral veins resulting from fluid circulation. Subterranean habitats or extensive mining operations, if vast enough, could leave networks of tunnels or mined-out caverns. Even if collapsed or filled with sediment, these could theoretically leave distinct geological patterns or change stress fields detectable via seismic surveys. The most ambitious form of technofossil might be evidence of planetary-scale terraforming or geomorphological engineering. Could an ancient civilization have significantly altered ocean basins, reshaped mountain ranges, or drastically modified hydrological systems to create new rivers or lakes? While surface features would erode, the underlying structural alterations could potentially leave patterns that are anomalous to natural geological processes. How would an engineered mountain range differ geologically from a natural one after millions of years of erosion and metamorphism? Perhaps distinct structural patterns, anomalous fault lines, or unusual metamorphic zones might hint at a prior intelligent design, although such interpretations would be extremely difficult and ambiguous. Massive waste repositories designed for extreme longevity could also be considered deliberate or accidental technofossils. Imagine deeply buried facilities for industrial or nuclear waste, constructed with the intent of isolating hazardous materials for millions of years. The contents of such repositories, particularly unique radioactive isotopes or highly toxic industrial chemicals, would be highly anomalous to natural background levels, and their presence in such specific, isolated geological contexts could be a strong indicator of prior intelligence. Our own human civilization is currently creating such repositories for nuclear waste, which could be future technofossils. How might technofossils appear in a deep time context? They would almost certainly be highly degraded and transformed, not recognizable machines or intact structures. They might manifest as unusual mineral concentrations, where elements are found together in proportions or forms not typically seen in natural rock. They could appear as altered rock textures, where the original material has recrystallized but retains some subtle, textural anomaly or preferred orientation hinting at its former artificial structure. Unique chemical elements or isotopic ratios might be found within newly formed mineral formations, even if the original object is gone. Some highly altered technofossils might appear as ghost structures, faint outlines or patterns within rock that suggest a prior non-natural geometry or organization. Crucially, they would most likely be found deep within the crust, requiring extensive geological surveying, drilling, or seismic techniques for detection. The Anthropocene provides a real-world analogue for the kinds of materials we are leaving behind that could become future technofossils. Our ubiquitous concrete, its aggregates, and its unique chemistry will form a distinct geological layer. Microplastics are already pervasive in marine sediments. Synthetic mineral phases from industrial processes, like the unique crystalline forms of smelting slag, could persist. The radioactive isotopes from nuclear activity, though decaying, leave a clear signal. The massive scale of our deep mining efforts and extensive landfills are also creating unique geological formations. Even the Great Pacific Garbage Patch, if it were to sink and undergo lithification, might one day form a plastic-rich conglomerate rock layer. This helps us conceptualize the subtle and pervasive form an ancient technofossil might take. The challenges of identifying and differentiating technofossils from natural phenomena are enormous. The signal-to-noise ratio is overwhelmingly dominated by natural geological complexity. Many natural formations can mimic apparent order or anomalous chemistry, leading to ambiguity. Perhaps the greatest challenge is unfamiliarity. An alien or ancient technology might operate on principles we do not yet understand, making its remnants difficult to recognize even if they were present. Furthermore, if we find an anomaly, there is no direct reference point to confirm its artificial origin. How do you identify something as artificial when you have no other known examples from that era? Despite these immense hurdles, the concept of technofossils remains a valuable thought experiment. It pushes the boundaries of detectability guiding scientific inquiry into what could persist over vast geological timescales. It encourages us to re-examine existing geological data with fresh eyes and to develop new analytical techniques capable of identifying extremely subtle and long-lasting signatures. It is not about proving the existence of ancient civilizations, but about exploring the limits of scientific knowledge and challenging our assumptions about the uniqueness of human technological development on this dynamic planet. The realm of unusual discoveries, often termed out-of-place artifacts or UPART, encompasses a diverse collection of historical and modern reports that claim to reveal objects or traces of technology that appear to contradict established archaeological and geological timelines. These purported anomalies often suggest the existence of advanced human civilizations far earlier than currently accepted, or even pre-human intelligence. While such claims capture the imagination and challenge conventional understanding, critical scientific examination reveals that the vast majority are attributable to natural geological formations, misinterpretations, or in some cases, outright hoaxes. However, maintaining an open mind for rigorous investigation is paramount in science. The appeal of UPART claims is undeniable. They tap into a deep human curiosity about mysteries, a desire to challenge established narratives, and a fascination with unknown possibilities. The idea that sophisticated civilizations could have existed and vanished without a trace, leaving behind only tantalizing clues, resonates with a sense of wonder. Yet, scientific rigor demands that extraordinary claims require extraordinary evidence, and this evidence must withstand independent scrutiny and provide a better explanation than conventional scientific understanding. The methodology for evaluating UPART claims is rooted in the fundamental principles of the scientific method. First, claims must undergo scientific peer review. This involves presenting the purported discovery to other experts in geology, archaeology, paleontology, and materials science for independent verification and critical analysis. The context of the discovery is paramount. Where exactly was the object found? What were the surrounding geological layers? Is the dating of these layers reliable and consistent? A lack of proper contextual documentation often invalidates a claim from the outset. Detailed material analysis, including chemical composition, microscopic structure, and even isotopic analysis, can reveal the true nature and origin of the object. Crucially, the possibility of natural formation must be rigorously excluded. Can a known natural process create a similar object? This is often the key to debunking many UPART claims. Finally, the possibility of human error, misidentification, or deliberate deception through hoaxes must always be considered. Let us critically examine some of the most prominent and frequently cited UPART claims and their conventional scientific explanations. The Klerksdorp spheres, found in a pyrophyllite deposit near Ottosdal in South Africa, are often presented as evidence of artificial manufacture predating human existence by billions of years. These small, spherical or disc-shaped objects, sometimes with concentric grooves, are highly compelling visually due to their near-perfect symmetry. However, geological analysis confirms them to be naturally formed concretions. Concretions are hard, compact masses of mineral matter that form within sedimentary rocks when minerals precipitate around a nucleus. They often grow concentrically, creating spherical shapes. The grooves sometimes observed are a result of the layering of the mineral growth or subsequent geological processes. These are well understood natural geological phenomena, common in various rock types around the world, and do not require an artificial explanation. The Antikythera mechanism, discovered in a shipwreck off the coast of Greece in 1901, is a genuine ancient artifact that has sometimes been presented as too advanced for its time, suggesting an unexplained leap in ancient technology. Dating to around the 1st century BCE, it is an intricate bronze mechanism composed of dozens of meshing gears. Initial interpretations were limited, but modern X-ray tomography and detailed study have revealed it to be a sophisticated astronomical calculator. It accurately predicted the positions of celestial bodies, phases of the moon, eclipses, and even Olympic game cycles. While incredibly complex and certainly a testament to the advanced engineering capabilities of ancient Greeks, it is not out of place in the context of their known mathematical and mechanical prowess. It demonstrates the peak of Hellenistic engineering and scientific understanding, not pre-human intelligence or inexplicable technology. Its existence informs us about the sophistication achievable within a human civilization of that era, challenging simplistic views of ancient technology, but not breaking the known timeline. The Iron Pillar of Delhi in India, standing over 7 meters tall and weighing more than 6 tons, is a metallurgical marvel from the 4th century CE. Its remarkable resistance to rust has led some to claim it as evidence of advanced, even impossible, metallurgy for its time. However, scientific analysis has revealed the secret to its durability. The pillar's rust resistance is due to its high phosphorus content, which forms a protective passive layer of amorphous iron, hydrogen phosphate hydrate on its surface, when exposed to the specific environmental conditions of Delhi, a humid atmosphere followed by dry periods. This protective layer continuously reforms, preventing further corrosion. This represents a highly sophisticated but achievable metallurgical understanding of the period, not an inexplicable anomaly. Its creation involved advanced forging and welding techniques for its time, but not metallurgy beyond human capability. The Baghdad battery is a clay jar containing a copper cylinder and an iron rod, discovered in Iraq and dating to the Parthian period around the 2nd century CE. It was controversially suggested to be an ancient electrical battery. While it is technically possible to generate a small voltage from such an arrangement if filled with an electrolyte like grape juice, there is no conclusive archaeological evidence to support its use as a battery. More conventional interpretations suggest it was used for storing sacred scrolls, which would have been kept moist, or as a jar for a metal rod, possibly for some form of electroplating, though direct evidence for widespread electroplating in that period is thin. Even if it were a battery, ancient knowledge of electroplating is itself an advanced human technology, but not out of place or indicative of a pre-human civilization. Claims of human-like footprints in rock formations hundreds of millions of years old, such as those reported in Coahuila, Mexico or Paluxy River, Texas, are often presented as definitive UPART. However, extensive geological and paleontological investigations have consistently attributed these to misidentified erosion patterns, natural geological formations, or dinosaur footprints that have been misinterpreted as human. The geology of these sites, when rigorously examined, does not support the age claims for human-like prints. Experts in ichnology, the study of trace fossils, can differentiate between various types of tracks and explain how natural weathering or specific animal gaits can create misleading patterns. There is no scientifically accepted evidence of human or human-like footprints in geological strata older than a few million years. The Coso artifact found in California in 1961 was a spark plug encased within what appeared to be a geode, claimed to be 500,000 years old. This sensational claim gained wide publicity. However, subsequent examination revealed that the geode was a common iron oxide concretion, which can form relatively rapidly around existing objects in certain soil conditions. The object inside was unequivocally a 20th century spark plug. The context of its discovery was likely a surface deposit, where a modern object became rapidly encased, rather than a truly ancient geological formation. Such concretions can form over decades or centuries, not necessarily millions of years, depending on the mineral-rich groundwater conditions. The Kingoody hammer, discovered in Scotland in the 19th century, was a hammerhead found partially embedded in sandstone, claimed to be hundreds of millions of years old due to the age of the rock. Scientific analysis revealed it to be an ordinary miner's hammer of a design consistent with 19th century tools. The most plausible explanation is that the hammer likely fell into an existing crack or fissure in the sandstone, or was left behind in a mine shaft, and was subsequently cemented in place by the slow deposition of minerals from groundwater. Its presence within the sandstone does not imply that it formed concurrently with the rock's original deposition. Claims of human remains or artifacts found in very old geological strata, such as the supposed Malachite Man or Guadalupe Man in the USA, similarly fall into the category of misinterpretations. These typically involve burials or intrusions where later human remains are interred into older layers of soil or rock, leading to a false appearance of great age. The principles of stratigraphy state that if a burial shaft cuts through older layers, the buried object is younger than those layers. Disturbances to soil and rock layers through digging animal burrows or natural processes can also lead to misinterpretations of age. Rigorous archaeological excavation and geological analysis can usually identify such disturbances and correctly date the remains. The alleged Precambrian screw, or spring, found in ancient rocks in Russia, are often circulated as evidence of advanced technology from billions of years ago. These objects, which visually resemble screws or springs, are almost universally identified by geologists and paleontologists as fossils of crinoids or sea lilies. Crinoids are marine animals that often have segmented stems, which when fossilized can break apart into disc-shaped or screw-like sections. Their helical or spiral patterns are entirely natural biological formations, not artificial mechanisms. The visual similarity is a case of pareidolia, where the human brain perceives familiar patterns in random or natural formations. The Baigong pipes in China are another notable claim. These are metal pipes found in a cave in Qinghai province, attributed by some to ancient aliens or a lost civilization due to their unusual composition and placement. However, geological investigations suggest they are natural geological formations, likely iron-rich concretions or fossilized tree roots that have formed tube-like structures. Natural processes can create surprisingly regular or pipe-like formations through mineral precipitation, around organic material, or within fractures in rock. The discovery of ancient figurines or other artifacts supposedly found in very old strata, such as a metallic vase claimed from tertiary coal in Massachusetts or a gold chain in Illinois coal, are typically explained by similar principles. These are often misidentified natural concretions, erosional forms that coincidentally resemble artificial objects, or instances where human artifacts have fallen into existing cracks or fissures in rock, or were part of a later mining debris that was mistakenly associated with the age of the coal seam. The conditions for an artifact to be genuinely embedded in a coal seam from its formation period are virtually impossible given the age of coal and the materials involved. The role of misinterpretation is central to many UPART claims. The human tendency for pareidolia, where the brain perceives familiar patterns in random stimuli, often leads individuals to see artificial designs in natural rock formations. A weathered rock might resemble a face or a tool, but a closer scientific examination reveals it to be purely geological. The problem of hoaxes is also a factor, where individuals deliberately fabricate or plant objects to mislead or gain notoriety or financial benefit. Science demands transparency and reproducibility to guard against such deception. While virtually all UPART claims have conventional scientific explanations, it is crucial for science to maintain an open-minded yet skeptical approach. New evidence, if truly extraordinary and rigorously verified, should be capable of challenging established paradigms. The scientific method is self-correcting. It demands extraordinary evidence for extraordinary claims, and this evidence must withstand repeated testing and independent verification. The value of these claims, even when debunked, is that they push scientists to re-examine existing data, refine dating techniques, and better understand the myriad ways natural geological processes can create unusual formations. They highlight public interest in deep history and the unknown, driving continued scientific exploration. However, the distinction must always be clear between unsubstantiated claims and testable scientific hypotheses. UPART claims are generally based on supposed direct, recognizable artifacts found out of place in time, while the concept of technofossils focuses on hypothetical, highly altered indirect chemical or mineralogical signatures. The approach to investigating them is fundamentally different, with technofossils seeking subtle, pervasive, and chemically stable planetary scale imprints rather than intact objects. Plate tectonics is the overarching geological theory that explains the large-scale motion of Earth's lithosphere, the rigid outermost shell of our planet. This lithosphere is broken into a mosaic of huge, irregular plates, which are constantly moving relative to one another. This incessant movement, driven by forces deep within the Earth, is the primary mechanism responsible for reshaping continents, opening and closing ocean basins, building mountain ranges, and crucially erasing vast amounts of ancient evidence over millions of years. Understanding the relentless destructive power of plate tectonics is fundamental to appreciating the immense challenge of finding any remnants of a pre-human advanced civilization. The Earth's interior is not static. Beneath the lithosphere lies the asthenosphere, a layer of the upper mantle that behaves like a very viscous fluid. Heat generated from the decay of radioactive elements within the Earth's core and mantle drives convection currents in this asthenosphere. Hotter, less dense material rises towards the surface, while cooler, more dense material sinks. These slow but powerful convection currents effectively drag the overlying lithospheric plates across the Earth's surface. The rates of plate movement are slow by human standards, typically a few centimeters per year, about the same speed as fingernail growth. However, over millions of years, these seemingly tiny movements accumulate into truly monumental changes, transforming the face of the planet. There are three main types of plate boundaries, each characterized by different interactions and associated geological phenomena. Divergent plate boundaries are where plates move away from each other. In oceanic settings, this leads to the formation of mid-ocean ridges, vast underwater mountain ranges where new oceanic crust is continuously generated by rising magma. This process, known as seafloor spreading, creates new lithosphere. In continental settings, divergent boundaries can lead to rift valleys, where continents begin to pull apart, eventually potentially forming new ocean basins. While new crust is formed here, this new crust is inherently young, and its creation implies that older crust must be destroyed elsewhere. Convergent plate boundaries are where plates move towards each other. These are the most geologically active and destructive boundaries for preserving ancient evidence. There are three subtypes of convergent boundaries. First, when an oceanic plate collides with a continental plate, the denser oceanic plate is forced to slide beneath the lighter, continental plate in a process called subduction. This creates deep oceanic trenches and often leads to the formation of volcanic arcs on the overriding continental plate. Second, when two oceanic plates collide, one oceanic plate subducts beneath the other, forming an oceanic trench and an island arc, a chain of volcanic islands. Third, when two continental plates collide, neither plate is significantly denser than the other, so neither truly subducts. Instead, the immense compressional forces cause the continental crust to buckle, fold, and thicken, leading to the formation of towering mountain ranges like the Himalayas, where the Indian plate is colliding with the Eurasian plate. Transform plate boundaries are where plates slide horizontally past each other. These boundaries are characterized by frequent earthquakes as the plates grind against each other. While they do not directly create or destroy crust on a large scale, they can offset features and cause significant local deformation. The most powerful mechanism for erasing ancient evidence is subduction. Oceanic crust formed at mid-ocean ridges is relatively thin and dense. As it moves away from the ridge, it cools and becomes even denser. When it encounters a less dense continental plate or another oceanic plate, it plunges back into the Earth's mantle at a subduction zone. This process is essentially a conveyor belt that recycles the oceanic lithosphere. The rate of subduction can vary, but is generally in the range of centimeters per year. Over millions of years, entire sections of ocean floor, hundreds or thousands of kilometers wide, can be completely consumed. The implications of subduction for any evidence of ancient civilizations are catastrophic. Imagine an advanced civilization that built cities or industrial complexes on a continent's coastline or on an oceanic island. If that coastline or island was situated on a subducting oceanic plate, or on the edge of a continental plate being overridden by an oceanic plate, its ultimate fate would be obliteration. As the oceanic plate descends into the mantle, any structures built upon it would be dragged down with it. They would be subjected to immense pressure and increasingly high temperatures. Materials would be crushed, deformed, melted, and chemically transformed beyond any hope of recognition. Steel would melt and become incorporated into the mantle silicates. Concrete would metamorphose. Plastics would decompose and their constituent elements would be dispersed. The entire physical record would be erased as the material is assimilated into the Earth's interior. This is why there is virtually no oceanic crust older than about 200 million years. Any civilization that existed on the ocean floor or on islands within ocean basins older than this time frame would have been completely wiped from the geological record by subduction. Even for civilizations on continental crust, subduction poses a threat, albeit in a different way. While continental crust is generally too buoyant to subduct deep into the mantle, it can be caught in zones of intense compression at convergent boundaries. When two continental plates collide, the immense forces crumple and deform the crust. The rock layers are intensely folded, fractured and uplifted, creating vast mountain ranges. Any structures caught within these collision zones would be subjected to unimaginable pressures. They would be crushed, flattened and incorporated into the deforming rock mass. The heat and pressure associated with mountain building also cause metamorphism, where existing rocks are transformed into new metamorphic rock types. During this process, the original mineralogy, texture and structure are completely altered. A city built of stone and metal would become an unrecognizable jumble of highly metamorphosed minerals with no hint of its original artificial form. Even if some distinct chemical signature persisted, it would be diffused and dispersed within a vast volume of highly altered rock, making its detection and interpretation exceedingly difficult. The Himalayan mountain range, for instance, is a product of such a collision, and its rocks contain highly deformed and metamorphosed remnants of ancient crustal materials, but not discernible structures. Beyond direct subduction and collision, the constant reshaping of continents over millions of years fundamentally alters the Earth's surface and the potential for preserving ancient evidence. Continents drift across the globe, changing their positions relative to the poles and the equator. This continental drift leads to dramatic changes in global climate patterns, ocean currents and sea levels. A landmass that was once in a tropical zone might move to a polar region, becoming covered by glaciers. A region that was once an arid desert might become a lush forest. These climatic shifts cause changes in erosion and sedimentation patterns, further obscuring ancient landscapes and any structures on them. The opening and closing of ocean basins is another long-term effect of plate tectonics that eradicates evidence. As continents rift apart, new oceans form. As continents collide, ancient oceans close. The rock record within these transient oceans is lost to subduction. When continents collide, the marine sediments and volcanic rocks of the intervening ocean basin are often intensely deformed and uplifted, becoming part of the new mountain range. While some scraps of ancient oceanic crust can be preserved as ophiolites within mountain belts, these are highly altered and fragmented, offering little hope of preserving civilization-level structures. Consider the dynamic cycle of the Wilson cycle, which describes the cyclical opening and closing of ocean basins over hundreds of millions of years. This cycle ensures that continental configurations are constantly changing from supercontinents breaking apart to new oceans forming and then closing to form new supercontinents. Each phase of this cycle is accompanied by immense geological activity, including massive volcanism, mountain building, and widespread erosion. Over a single Wilson cycle, which can last 500 million years, the entire surface of the Earth is fundamentally reconfigured. This constant planetary scale churn makes the long-term preservation of any surface-based civilization extremely unlikely. Volcanism associated with plate boundaries also contributes to the destruction and burial of ancient evidence. At subduction zones, rising magma can lead to explosive volcanic eruptions that bury vast areas under layers of ash and lava. While burial might initially protect structures from surface erosion, subsequent geological processes like compaction metamorphism and further volcanism would likely destroy any recognizable forms. The ash and lava would also rapidly alter the chemistry of the immediate environment, further obscuring any distinct artificial signatures. Earthquakes, a direct consequence of plate movement, can cause widespread destruction to artificial structures. While individual earthquakes are temporary events, over millions of years, the cumulative effect of seismic activity at active plate boundaries can contribute significantly to the breakdown and collapse of buildings and infrastructure, reducing them to rubble that then becomes subject to further geological processes. A city located on an active fault line would be continuously subjected to seismic stress, making its long-term preservation improbable. The net effect of plate tectonics is a planetary scale recycling system. No part of the Earth's surface is truly static or immune from the forces of creation and destruction over millions of years. Old crust is destroyed, new crust is formed, and continents are constantly on the move. This constant churn ensures that the geological record is heavily filtered and incomplete. The older the rock, the less likely it is to be preserved, and the more likely it is to have been subjected to multiple cycles of deformation, heating, and erosion. This means that for periods hundreds of millions of years in the past, the available geological record is increasingly sparse and highly altered. For a hypothetical ancient civilization, the implications are severe. A civilization that existed on a continental landmass, say 300 million years ago, would have had its footprint subjected to unimaginable stresses. Its cities might have been buried under kilometers of sediment, only to be uplifted later and eroded away, or caught in a continental collision, metamorphosed into unrecognizably altered rock. If it existed on an oceanic plate, its entire physical footprint would have been subducted and melted back into the mantle. Even if industrial byproducts like unique chemical signatures were produced, these too would be subject to dispersal dilution and chemical alteration within the Earth's dynamic systems, making their identification as artificial, rather than natural anomalies, incredibly challenging. The unlikeliness of finding coherent physical evidence of an ancient civilization due to plate tectonics cannot be overstated. We are not just talking about surface erosion, but the wholesale reprocessing of vast volumes of Earth's crust. This geological machinery works efficiently over deep time to erase old records and present new ones. The limited geological record that does survive from deep time often shows intense deformation and metamorphism, which would utterly destroy any delicate structures or complex materials. The sheer power and scale of plate tectonic processes make them the ultimate eraser of ancient surface history, presenting an almost insurmountable barrier to the detection of any pre-human civilization's physical legacy. Erosion and weathering are relentless and pervasive geological forces that constantly reshape the Earth's surface. They are the primary sculptors of landscapes, wearing down mountains, carving valleys, and redistributing vast quantities of material across the globe. For any discussion of finding evidence of ancient civilizations, these processes represent an immense destructive power, effectively erasing surface features including any artificial structures over geological timescales and making localized detection exceedingly difficult. Weathering is the process by which rocks and minerals are broken down at or near the Earth's surface. It is the initial step in the destructive cycle, preparing material for transport. Weathering is broadly divided into two main categories: physical or mechanical weathering and chemical weathering. Both types work in tandem, often accelerating each other's effects. Physical weathering involves the mechanical breakdown of rocks into smaller fragments without changing their chemical composition. One of the most effective forms is freeze-thaw or frost wedging. Water seeps into cracks and fissures in rocks. When temperatures drop below freezing, the water turns into ice, which expands by about 9%. This expansion exerts enormous pressure on the rock, widening the cracks. Repeated cycles of freezing and thawing gradually pry apart the rock, breaking it into smaller pieces. This process is particularly effective in temperate and polar regions, where temperatures frequently fluctuate around freezing point. For artificial structures, this means concrete can crack, masonry can be pried apart, and foundations can be destabilized. Another form of physical weathering is salt crystal growth. In arid or coastal environments, salty water penetrates rock pores and cracks. As the water evaporates, salt crystals grow, exerting pressure that pries apart rock grains and breaks off flakes or chunks. This is a common cause of deterioration in stone buildings in dry climates or near the sea. Exfoliation or unloading occurs when overlying rocks or sediments are removed by erosion, releasing the pressure on the underlying rock. This causes the rock to expand and crack in layers parallel to the surface, creating onion-like sheets that peel away. This process can break down large rock masses over time. Thermal expansion and contraction occur due to daily or seasonal temperature changes. As rocks heat up, they expand, and as they cool, they contract. Different minerals within a rock expand and contract at different rates, creating internal stresses that can eventually cause the rock to fracture. While less effective than freeze-thaw, it contributes to the overall breakdown, particularly in deserts with large diurnal temperature swings. Biological activity also contributes to physical weathering. Plant roots growing into cracks can exert significant pressure, widening them and breaking rocks apart, a process known as root wedging. Burrowing animals can also excavate and disturb soil and rock, exposing fresh surfaces to further weathering. Lichens and mosses growing on rock surfaces can also contribute to chemical weathering by producing acids. For artificial structures, Vegetation growing through cracks in pavement or foundations can lead to rapid structural failure. Chemical weathering involves the decomposition of rocks and minerals through chemical reactions, changing their composition. One common process is dissolution, where minerals dissolve in water. For example, limestone and marble, which are primarily composed of calcium carbonate, readily dissolve in slightly acidic rainwater, leading to the formation of caves and the erosion of statues and buildings. Hydrolysis is a reaction where water molecules react with minerals, particularly silicates, which are the most common minerals in the Earth's crust. This reaction alters the minerals into new compounds, often clay minerals. For example, feldspar, a common mineral in granite, weathers into clay through hydrolysis. This process weakens the rock significantly, making it more susceptible to physical breakdown. Oxidation is a reaction where minerals react with oxygen, often in the presence of water. Iron-rich minerals are particularly susceptible to oxidation, forming various iron oxides or rust. This process weakens the rock and gives it a characteristic reddish or yellowish-brown stain. Metal structures like steel beams would completely oxidize over time, turning into dispersed rust. Carbonation is a specific type of dissolution where carbon dioxide dissolved in water forms carbonic acid. This weak acid reacts with carbonate minerals like calcite in limestone, dissolving them. This process is naturally occurring but can be accelerated by anthropogenic carbon dioxide in the atmosphere, leading to acid rain, which severely degrades stone buildings and monuments. Erosion is the process by which weathered material is transported from one place to another. Once rocks are broken down by weathering, various agents of erosion pick up and carry away the fragments. Water is arguably the most powerful agent of erosion. Raindrops directly detach soil particles. Sheet erosion removes thin layers of soil evenly across a slope. Rill and gully erosion occur as concentrated flows of water carve small channels and then larger trenches. Rivers are incredibly effective erosional agents. They erode their beds and banks through abrasion, where sediment carried by the water grinds away at the riverbed hydraulic action, where the force of the water dislodges particles, and solution where soluble minerals are dissolved. Over geological timescales, rivers carve out vast valleys and canyons, transporting immense quantities of sediment from mountains to oceans. Coastal erosion by waves and currents constantly reshapes shorelines, eroding cliffs and redistributing beach sands. Any coastal cities or structures would be relentlessly attacked by these forces. Wind erosion is significant in arid and semi-arid regions. It can pick up loose sand and dust particles through deflation, and abrade rock surfaces through sandblasting, a process called abrasion. Wind erosion can remove vast quantities of fine sediment and shape landforms like sand dunes and desert pavements. For artificial structures exposed to wind erosion, surfaces would be slowly worn away and foundations could be undermined. Glacial erosion occurs as massive sheets of ice move slowly across the landscape. Glaciers erode through plucking, where ice freezes onto rock fragments and pulls them away, and abrasion, where rocks embedded in the ice grind against the underlying bedrock. Glaciers are incredibly powerful, sculpting U-shaped valleys, creating cirques and fjords and scouring away vast amounts of material. During repeated ice ages over millions of years, vast areas of continents are subjected to intense glacial erosion, effectively bulldozing away any surface features, including any ancient structures. Gravity also plays a role in erosion through mass-wasting processes such as landslides, rockfalls, and mudslides. These rapid downslope movements of rock and soil can quickly destroy and bury localized areas. While often localized, their cumulative effect over millions of years contributes to the breakdown and redistribution of surface material. The interplay of weathering and erosion is a continuous and pervasive cycle. Weathering breaks down rock, creating smaller particles. Erosion then transports these particles, often depositing them in new locations where they can accumulate to form sedimentary layers. This process of sedimentation leads to burial, which initially protects material from surface erosion, but then subjects it to new forces of transformation. As more layers accumulate, the pressure on buried material increases, causing compaction. Groundwater can then cement these particles together, forming new sedimentary rocks. Over geological time, buried sediments are subjected to increasing temperatures and pressures, leading to diagenesis and eventually metamorphism, which can fundamentally alter the original materials. The rates of erosion, while seemingly slow on a human timescale, are incredibly effective over millions of years. A mountain range might take tens of millions of years to form, but it will also take tens of millions of years to be completely eroded away. The Himalayas, still growing, are simultaneously being eroded. The entire surface of the Earth is constantly being worn down and reshaped. Even hard, resistant rocks are eventually broken down and transported. This means that no surface feature, including any artificial structure, is truly permanent over geological epochs. The impact of these relentless forces on any ancient structures or evidence of a pre-human civilization would be devastating. First, surface obliteration is almost guaranteed. Anything built on the Earth's surface, whether a city, a road, or a monument, would be relentlessly attacked by wind, water, and ice. Over millions of years, these forces would wear down even the most massive constructions, reducing them to scattered fragments, and eventually to their constituent mineral grains. No matter how grand the scale, surface structures cannot withstand these forces indefinitely. Second, the dispersal of materials would make localized detection exceedingly difficult. Even if materials from an ancient industrial process were initially concentrated, erosion would transport them over vast areas, diluting their signal. A factory's waste products, initially localized, would be spread out across river systems, ocean basins, or carried by wind currents globally. While this might create a faint, widespread chemical signature, it would eliminate any localized physical evidence. Third, there would be a complete loss of coherence for structures. Buildings and infrastructure would not just disappear, they would be disaggregated into individual particles. A concrete building would become sand and gravel. A steel bridge would become rust particles. The original coherent form and engineered arrangement would be utterly lost, making it impossible to identify the remnants as a former artificial structure. Fourth, the record itself is incomplete. Erosion is not always balanced by sedimentation in a given area. Periods of extensive erosion create gaps in the geological record known as unconformities. This means that large swathes of Earth's history in specific locations are simply missing from the rock record, further reducing the chances of finding any rare ancient evidence. Finally, even if structures were rapidly buried and protected from surface erosion, they would then be subjected to the processes of diagenesis and metamorphism. As discussed previously, these processes involve immense pressure and heat, fundamentally altering the chemical composition and crystalline structure of materials. A buried building would not remain a building. Its components would be crushed, dissolved, recrystallized, and chemically transformed into new minerals, effectively becoming indistinguishable from natural rock components. The original artificial design would be completely obliterated. Consider our own modern infrastructure. Our great dams, bridges, and cities seem immense and permanent to us. However, without constant maintenance, even these would degrade within centuries or millennia. Projecting this degradation over millions of years, the outcome is clear: complete physical obliteration and dispersal. The concrete crumbles, the steel rusts, the roads break apart. The material is then subjected to the full force of weathering and erosion, eventually becoming sediment and then potentially rock, losing all vestiges of its engineered form. Biological degradation is the pervasive and incredibly efficient process by which organic materials are broken down by living organisms, primarily microorganisms like bacteria and fungi, but also by scavengers and detritivores. This natural cycle of decomposition is fundamental to life on Earth recycling nutrients and preventing the accumulation of vast quantities of dead organic matter. However, for any discussion of preserving traces of ancient civilizations, biological degradation poses a formidable barrier, rapidly consuming most organic materials associated with the society and causing them to disappear without a trace within relatively short geological periods. At its core, decomposition is a series of complex biochemical reactions. The rate and pathways of degradation depend heavily on environmental conditions, particularly the presence or absence of oxygen. Aerobic decomposition, occurring in the presence of oxygen, is the most efficient and common form of decay. Oxygen-loving bacteria and fungi act as decomposers, breaking down complex organic molecules such as proteins, carbohydrates, and lipids into simpler compounds. This process releases energy for the microorganisms and results in the production of carbon dioxide, water, and inorganic nutrients. In well-aerated environments like most terrestrial soils or shallow oxygen, rich waters, decomposition is rapid and thorough. A dead animal or plant will quickly be consumed and broken down until only very resistant components remain, or nothing at all. This rapid breakdown means that most organic material is recycled into the ecosystem within days, weeks, or months. For a civilization, this implies that organic artifacts like wooden structures, textiles made from natural fibers, food remains, and paper would swiftly vanish if exposed to normal atmospheric or aquatic conditions. Their structural integrity would be lost, and their chemical components would be dispersed. Anaerobic decomposition, occurring in the absence of oxygen, is a slower but still effective process. In oxygen-deprived environments such as deep muds, stagnant bogs, or the anoxic bottom waters of some lakes and oceans, different types of microorganisms thrive. These anaerobic bacteria obtain energy by breaking down organic matter without oxygen, often producing byproducts like methane, hydrogen, sulfide, or various organic acids. While slower than aerobic decay, anaerobic decomposition can still lead to the complete breakdown of complex organic molecules over longer timescales, typically hundreds or thousands of years for most materials. The distinct chemical signatures of anaerobic environments, such as the smell of rotten eggs from hydrogen sulfide, are characteristic of these decay pathways. Beyond microorganisms, larger organisms also contribute to biological degradation. Scavengers like insects, birds, and mammals consume dead organic remains, physically breaking them apart and accelerating their decomposition. Detritivores such as worms, millipedes, and certain insect larvae feed on decaying organic matter, further fragmenting it and incorporating it into the soil. This combined biological activity ensures that the vast majority of organic material is rapidly recycled into the ecosystem, leaving no persistent physical trace. Let us examine specific types of organic materials associated with a civilization and their likely degradation pathways. Soft tissues, comprising the vast majority of an organism's body, are among the most rapidly degrading organic materials. Muscles, organ skin, and other soft parts are quickly broken down by enzymes released from the organism itself, a process called autolysis, and then by a host of bacteria and fungi. Putrefaction, the bacterial decomposition of proteins, leads to the production of various gases and a foul odour. Unless exceptionally rapid burial and anoxic conditions occur, the physical bodies of a civilization's inhabitants would almost entirely decompose within a relatively short period, often within weeks or months. This explains why the vast majority of creatures that have ever lived, including human ancestors, have left no fossilized remains of their soft bodies. Only skeletal elements with their hard mineralized components have any chance of long-term preservation. Wood, a primary building material for many civilizations, is composed primarily of cellulose and lignin. While wood can be quite durable in dry or oxygen-deprived conditions, it is highly susceptible to decay in moist, oxygenated environments. Fungi, particularly wood-rotting fungi, are highly efficient at breaking down cellulose and lignin, turning wood into crumbly dust. Various species of bacteria and wood-boring insects like termites and beetles also contribute significantly to its degradation. The resistance to decay varies among different wood types, but all wood eventually succumbs to biological attack. A wooden building, if abandoned, would typically rot and collapse within decades or centuries unless special preservation conditions were met. Natural textiles such as cotton wool and silk are organic fibers that are readily biodegradable. Cotton and linen are cellulose-based and subject to bacterial and fungal attack. Wool and silk are protein-based and can also be degraded by microorganisms and certain insects. An abandoned textile garment would rapidly decompose within years or decades. Leather, hair, and feathers are composed primarily of keratin and collagen, which are more resistant to decay than muscle tissue, but are still highly susceptible to bacterial and fungal attack. While these can persist for longer periods under specific conditions, they are far from immune to biological degradation over geological timescales. Plastics, often considered highly durable, are not entirely immune to biological degradation, although their degradation rates are significantly slower than natural organic materials. While many common plastics are designed to be resistant to microbial attack, microbes capable of degrading various types of plastics are increasingly being discovered. Furthermore, most plastics are susceptible to photodegradation, where ultraviolet light from the sun breaks down their chemical bonds, making them brittle and causing them to fragment into smaller pieces. These larger fragments then break down into microplastics and eventually nanoplastics. Even persistent plastics eventually fragment, losing their macroscopic integrity. While microplastics might leave a diffuse chemical signature in the geological record, the original macroscopic artifact would be completely lost due to biological and environmental breakdown. Rubber, both natural and synthetic, also degrades through oxidation and microbial action. Paper and books made of cellulose are highly susceptible to moisture mold and insect damage, disintegrating quickly unless kept in highly controlled environments. The rarity of preservation conditions is a critical factor limiting the fossil record of organic materials. To overcome rapid biological degradation, exceptional circumstances are required. Anoxia or oxygen deprivation is the single most important factor. Environments where oxygen levels are extremely low or absent, such as stagnant bogs, deep ocean basins, a noxic lake, bottom sediments, or fine muds where rapid burial cuts off oxygen supply, inhibit the activity of oxygen-loving aerobic decomposers. In such environments, organic matter can persist for much longer periods, sometimes for thousands or even millions of years if other conditions are also met. For example, some exceptionally well-preserved remains have been found in peat bogs, which are highly acidic and anoxic. Rapid burial also plays a crucial role. If organic remains are buried quickly by fine sediment, they are protected from scavengers and many physical forces, and the rapid burial itself can help to establish anoxic conditions by cutting off oxygen supply. This is why many marine fossils are found in fine-grained mudstones. Extreme environments can also aid preservation. Desiccation or extreme dryness can lead to mummification, where the lack of moisture inhibits microbial activity. This is limited to very arid environments like deserts, and can preserve organic material for thousands of years. Extreme cold, such as in permafrost regions, significantly slows down all biological and chemical processes, preserving organic remains like woolly mammoths for tens of thousands of years. High salinity in environments like salt flats or highly saline lakes can also inhibit the growth of many microbes, aiding preservation. Ultimately, for organic structures to survive for millions of years, they must undergo mineralization or petrification. This is not strictly biological degradation, but the process by which organic material is replaced by minerals from groundwater, effectively turning it into stone. This requires specific geochemical conditions where mineral-rich fluids permeate the buried organic matter, replacing it cell by cell or molecule by molecule. This is the only realistic way for organic structures to leave a persistent structural trace over deep time, but it means the original organic material itself is gone, replaced by an inorganic replica. The consequences for civilization traces are profound. The vast majority of organic materials associated with a civilization, including clothing, furniture, food, wooden tools, books, and many building components, would vanish without a trace due to biological degradation. The physical bodies of the civilization's inhabitants would almost entirely decompose, leaving only the rarest and most specific conditions for the preservation of skeletal remains. This means that reconstructing the daily life, art, and societal structures of an ancient civilization would be incredibly difficult without any organic artifacts. The record would be heavily biased towards inorganic materials and the most exceptional preservation sites. Biological degradation operates on human and historical timescales, not geological ones. Most organic matter disappears within years or decades. Under very rare and specific conditions, preservation for thousands or a few tens of thousands of years is possible, as seen in peat bogs or permafrost. However, preservation for millions of years effectively guarantees complete biological degradation unless the material is entirely replaced by minerals. Even very slowly degrading plastics would, over millions of years, break down into their constituent molecules or diffuse chemical signals, losing their macroscopic integrity. The ultimate fate of massive amounts of organic material under specific conditions of anoxia, burial, heat, and pressure is transformation into kerogen, oil, or coal. This is the process that forms fossil fuels, which are themselves a record of ancient organic life. However, this transformation involves the complete loss of original biological or artificial structure. An ancient plastic, if buried and subjected to these conditions, might contribute to the formation of kerogen or leave a diffuse chemical signal in the resulting hydrocarbons, but it would not persist as a recognizable plastic artifact. This process means that while organic byproducts might contribute to a broader geochemical signature, they would not be physical objects. Biological degradation often works in tandem with other destructive forces like weathering and erosion, accelerating the removal of organic materials from the Earth's surface and near-surface layers. This combined action ensures that the vast majority of organic traces of any past civilization would be effectively and rapidly erased, leaving behind an extremely limited and highly biased record for geological time. Large-scale catastrophic events are sudden and devastating natural phenomena that can cause widespread destruction and profoundly impact the preservation of any societal infrastructure on Earth. Over millions of years, Earth has experienced numerous such events, each capable of obliterating existing life and landscapes, and thus serving as a formidable eraser of any potential evidence of ancient civilizations. Understanding the nature and scale of these catastrophes is crucial for appreciating the extreme unlikelihood of finding intact remains from a bygone era. Supervolcanic eruptions represent one of the most powerful and destructive types of terrestrial catastrophes. A supervolcano is defined by an eruption with a volcanic explosivity index, or VEI, of 8, indicating an eruption that expels more than 1,000 cubic kilometers of material. Examples include the Toba eruption, approximately 74,000 years ago, and the Yellowstone caldera eruptions hundreds of thousands to millions of years ago. The immediate impacts of such an eruption are apocalyptic. Pyroclastic flows, fast-moving superheated avalanches of gas and ash can travel hundreds of kilometers, incinerating and burying everything in their path. Widespread ashfall can blanket continents, causing structures to collapse under the sheer weight of the material. Lahars, destructive mudflows composed of volcanic ash and water, can inundate vast valleys and bury entire towns. In the immediate vicinity of such an eruption, any existing societal infrastructure would be totally obliterated and deeply buried. Beyond the immediate devastation, supervolcanic eruptions have profound global and long-term environmental and climatic impacts. Massive amounts of ash and sulfur dioxide are injected into the stratosphere. The ash clouds can block sunlight, leading to a volcanic winter with global temperature drops and widespread crop failures. The sulfur dioxide reacts with water vapor to form sulfuric acid aerosols, leading to extensive acid rain that could devastate ecosystems and accelerate the corrosion of any exposed structures. While these eruptions eventually subside, the climate disruption can persist for years or even decades, leading to societal collapse far from the eruption site due to agricultural failure and mass starvation. Geologically, these events leave massive ignimbrite deposits, hardened ash flows, and widespread distinct ash layers that can serve as crucial time markers in the geological record, but they mark a period of immense destruction rather than preservation. Major asteroid and comet impacts are another class of catastrophic events with global destructive potential. While rare on geological timescales for planet-killer-sized objects, smaller but still devastating impacts occur more frequently, capable of causing regional devastation. The most famous example is the impact event approximately 66 million years ago that led to the extinction of the non-avian dinosaurs and many other life forms. The immediate impacts of such an event are immense. The sheer energy released at impact is equivalent to many nuclear bombs, instantly vaporizing rock and water, creating powerful shockwaves that propagate globally. If the impact occurs in an ocean, it generates colossal tsunamis that can inundate vast coastal areas. Material ejected from the impact site is thrown into the atmosphere globally, causing an impact winter as sunlight is blocked. Re-entering ejecta can cause widespread global wildfires, turning continents into infernos. The long-term geological impact of such an event is a distinct geological signature, including a global iridium layer, an element rare on Earth's surface but common in meteorites. Other markers include shocked quartz, which is quartz grains deformed by extreme pressures, and tektites, which are small glassy beads formed from melted rock droplets. These geological markers are typically found globally in a specific layer, marking the timing of the catastrophic event. For any ancient civilization, a major asteroid impact would mean total annihilation of life and infrastructure at the impact site, followed by global environmental collapse leading to mass extinctions and societal breakdown far beyond the immediate impact zone. Even if some structures survived the initial blast, they would then face the global environmental catastrophe of darkness, cold, and acid rain, making continued societal function impossible. Prolonged ice ages or glaciations are recurring catastrophic climate shifts that profoundly reshape continental landscapes. Earth has experienced numerous major ice ages throughout its history, including the Quaternary glaciation over the last 2.6 million years, and even more extreme snowball Earth events in the Neoproterozoic era, where ice may have covered almost the entire planet. During an ice age, massive continental ice sheets, often kilometers thick, form and expand, covering vast portions of continents. The sheer weight and movement of these ice sheets act as gigantic bulldozers, scouring landscapes clean. Glaciers erode through plucking, where ice freezes onto rock fragments and pulls them away, and abrasion, where rocks embedded in the ice grind against the underlying bedrock. They carve out U-shaped valleys, create deep fjords, and scrape away vast amounts of surface material, including any structures or topsoil. The depositional impact of glaciers also contributes to destruction. As glaciers melt, they deposit unsorted debris called till and form distinctive landforms like moraines. While these deposits can bury some features, it is often with destructive force, and subsequent melting or movement can expose and destroy buried material. A key consequence of ice ages is massive sea level changes. As vast amounts of water are locked up in ice sheets, global sea levels can drop by over 100 meters, exposing vast areas of continental shelves as new land. Conversely, when the ice melts, sea levels rise rapidly, submerging previously exposed coastal areas. For any ancient civilization, prolonged ice ages would render vast landscapes uninhabitable, cause massive infrastructure destruction by the direct movement of ice sheets, and alternately submerge or expose and erode coastal cities. The extreme climate shifts would lead to widespread agricultural failure and force mass migrations, likely causing societal collapse. Rapid climate shifts that are not necessarily full ice ages can also be catastrophic for civilizations. These are abrupt and significant changes in global temperature precipitation patterns or ocean circulation that occur over decades or centuries rather than millennia. Such shifts can be naturally driven by factors like orbital variations, large volcanic eruptions, or changes in ocean currents, or in theory, potentially by an ancient civilization itself, through massive greenhouse gas releases. The impacts include rapid sea level rise or fall from thermal expansion or ice melt, widespread desertification in some regions and increased flooding in others, and shifts in climate zones that make traditional agriculture impossible. These changes would lead to widespread agricultural collapse, mass migrations, and societal destabilization as communities struggle to adapt to drastically altered environments. While not directly pulverizing infrastructure like an asteroid impact, rapid climate shifts could lead to the complete disintegration of organized society and the abandonment of infrastructure, leaving it vulnerable to subsequent degradation by weathering and erosion. For instance, rapid warming can lead to ocean anoxic events where vast parts of the ocean become oxygen depleted, causing widespread marine extinctions and resulting in layers of black shales in the geological record. Other more exotic catastrophic events have been hypothesized over geological timescales. Gamma-ray bursts originating from distant supernova explosions are extremely powerful cosmic events that could strip away Earth's protective ozone layer, leading to mass extinctions from increased ultraviolet radiation. While evidence for such events in Earth's deep past is still debated, they represent a potential, albeit rare, existential threat to life. Massive solar flares or coronal mass ejections from our own sun, while generally less destructive to the physical planet, could disrupt technology on a global scale, leading to a breakdown of technologically dependent societies. The cumulative effect of these catastrophic events over millions of years ensures a thorough destruction and obliteration of any ancient evidence. Earth's history is punctuated by these massive disturbances, each acting as a reset button for surface conditions and life. No single location on Earth is immune from all these types of events over deep time. A region might survive an asteroid impact only to be overridden by a glacier millions of years later. The consequences for preservation are dire. Catastrophic events cause direct destruction through physical pulverization, burial, or incineration. They also lead to societal collapse, which means the abandonment of infrastructure, leaving it vulnerable to subsequent degradation by slower but equally relentless forces like weathering and biological decay. The environment is transformed beyond recognition. While catastrophes often leave specific geological markers like ash layers or iridium layers, these are essentially tombstones indicating a destructive event rather than a detailed record of what was destroyed. The very existence of these markers points to the episodic and violent nature of Earth's history, which constantly erases and remixes its surface records, making the survival of any specific, highly organized ancient infrastructure overwhelmingly improbable. The anthropic principle is a concept in cosmology and philosophy that suggests the fundamental constants and physical laws of the universe appear to be precisely tuned for the existence of life, particularly intelligent life. It posits that our very existence as observers places constraints on the kinds of universes we can inhabit. In the context of advanced life on Earth, the anthropic principle leads to a profound inquiry, whether the unique conditions that have allowed for human evolution and the relatively late appearance of complex technologically capable life on our planet might suggest that such a development is inherently rare, perhaps even unique to this specific moment in Earth's long history. The anthropic principle is typically discussed in two main forms. The weak anthropic principle states that the observed values of all physical and cosmological quantities are not equally probable, but they take on values restricted by the requirement that there exist sites where carbon-based life can evolve, and by the requirement that the universe is old enough for it to have already done so. In simpler terms, we must observe a universe that is compatible with our existence, because if it were not, we would not be here to observe it. The strong anthropic principle goes further, suggesting that the universe must have properties that allow life to develop within it at some stage. For our current discussion, the weak anthropic principle is more directly relevant, as it forces us to consider the specific chain of events and conditions on Earth that made our own unique emergence possible. Earth's conditions are indeed remarkably unique and finely tuned for the development of complex life. Our planet resides in the habitable zone around the Sun, a region where temperatures allow for the sustained presence of liquid water on the surface. Liquid water is universally considered essential for life as we know it, acting as a solvent for biochemical reactions and a medium for transport. If Earth were slightly closer to the Sun, water would evaporate. Slightly farther, it would freeze solid. The Sun itself is a G-type main sequence star, a stable star that has provided consistent energy output for billions of years. Stars that are too large burn too quickly, while those too small might cause tidal locking or emit too much harmful radiation. Our Sun's stability has been crucial for the long evolutionary timescale needed for complex life to emerge. Earth's planetary mass and composition are also critical. Our planet is large enough to retain a substantial atmosphere, preventing its gases from escaping into space. Its internal heat, generated by radioactive decay, drives geological processes like plate tectonics. The right mix of heavy elements, forged in older stars, was necessary for the formation of a rocky planet with a solid core, mantle, and crust, providing the raw materials for life and geological activity. Plate tectonics is a particularly vital planetary feature for long-term habitability and the evolution of complex life. It regulates the global carbon cycle by recycling carbon from the atmosphere into rocks and back again over geological timescales, which helps to stabilize Earth's climate. Without plate tectonics, carbon dioxide would eventually be locked away in rocks, leading to a frozen planet. It also contributes to the creation of continents and diverse landforms, providing varied habitats for evolution. Furthermore, the convective motions in the Earth's molten outer core generate a powerful magnetic field. This magnetic field acts as a shield, deflecting harmful charged particles from the solar wind and cosmic rays, which would otherwise strip away the atmosphere and irradiate the surface. The sustained protection from this radiation allowed complex life to evolve safely over billions of years. The presence of a large moon, Earth's moon, is another unique condition. The moon's gravitational pull stabilizes Earth's axial tilt, preventing drastic and chaotic wobbles in its rotational axis. This stabilization ensures relatively stable seasons and climatic patterns over geological time, providing a consistent environment for evolutionary development. Without the moon, Earth's tilt could vary wildly, leading to extreme and unpredictable climate swings that might prevent the sustained evolution of complex life. The moon also generates strong tidal forces, which may have played a role in the emergence of life from the oceans onto land by creating intertidal zones. The role of Jupiter, the largest planet in our solar system, is also often highlighted as a protective factor. Jupiter's immense gravitational field acts as a cosmic bouncer, deflecting many comets and asteroids from the outer solar system that might otherwise impact Earth. While impacts have certainly occurred and caused mass extinctions, Jupiter's presence has likely reduced their frequency and severity, providing periods of relative calm necessary for complex life to flourish and evolve. The evolution of Earth's atmosphere composition was another prerequisite for advanced life. Early Earth's atmosphere was very different from today's oxygen-rich environment. The oxygenation of the atmosphere was primarily driven by the metabolic activity of early life forms, particularly cyanobacteria, which began performing photosynthesis billions of years ago. The Great Oxidation event, occurring around 2.4 billion years ago, dramatically increased atmospheric oxygen levels. This was a prerequisite for the evolution of complex animal life, which relies on aerobic respiration for energy. Without this biological transformation of the atmosphere, large energy-demanding organisms like humans could not have evolved. Finally, the unique properties of liquid water itself are fundamental. Its ability to dissolve a wide range of substances, its high heat capacity which moderates temperatures, and its anomalous expansion upon freezing, allowing ice to float and insulate water below, all contribute to making Earth a uniquely hospitable planet for life. The concept of fine-tuning extends beyond Earth's specific conditions to the fundamental constants of the universe. Physicists have argued that if fundamental constants such as the strength of the gravitational force, the electromagnetic force, the mass of the electron, or the cosmological constant were even slightly different, life as we know it would be impossible. For instance, if gravity were much stronger, stars would burn out too quickly. If it were weaker, galaxies might not form. Such arguments lead to the profound question of whether our existence is a mere coincidence, a statistical fluke, or indicative of deeper principles, perhaps even a multiverse where our universe is just one of many, each with different constants, and we simply happen to live in the one where the conditions are just right. Now, let us consider the evolutionary path to intelligence on Earth within this anthropic context. It is crucial to note that while life emerged relatively early in Earth's history, simple single-celled life forms dominated for billions of years. Multicellular life only appeared relatively recently, during the Phanerozoic Eon, which began approximately 541 million years ago. Large complex animals and plants emerged even more recently. This long incubation period for simple life suggests that the evolution of complexity itself is a major hurdle. Key evolutionary innovations were prerequisites for the eventual emergence of intelligence. Photosynthesis allowed life to harness solar energy, leading to the oxygenation of the atmosphere. The evolution of eukaryotic cells with their complex internal structures allowed for greater cellular complexity. Multicellularity enabled the development of specialized tissues and organs, leading to larger and more complex body plans. Sexual reproduction introduced genetic variation, accelerating evolution. The development of bilateral symmetry, nervous systems and internal skeletons provided the foundations for mobile complex animals. Each of these steps took millions of years and represented a significant evolutionary hurdle. The long reign of the dinosaurs, approximately 180 million years, further highlights the contingent nature of human intelligence. During this vast period, large complex animals dominated terrestrial ecosystems, yet no dinosaur civilization emerged. This suggests that simply having complex life does not automatically lead to technologically capable intelligence. Perhaps their evolutionary path favoured specialisation in size or strength, or the environmental conditions were not conducive to the specific type of intelligence that leads to technology. The KPE extinction event 66 million years ago, caused by a massive asteroid impact, is another pivotal moment for human evolution. This catastrophic event cleared ecological niches by eliminating the non-avian dinosaurs and many other life forms. This allowed for the rapid diversification and ascendancy of mammals, which had previously been relatively small and marginalised. If not for this event, it is plausible that human evolution might not have occurred, or would have taken a vastly different path. This suggests a highly contingent aspect to the emergence of human intelligence, implying that our existence is not a predetermined outcome of Earth's history, but a result of a specific chain of events. The evolutionary journey of primates and hominids further underscores the rarity and contingency of our development. The evolution of dexterity, highly acute vision, and complex social structures within primates laid crucial groundwork. The specific hominid lineage that led to humans embarked on a unique path beginning with bipedalism, which freed the hands for tool manipulation and energy-efficient locomotion. This was followed by a dramatic expansion of brain size over millions of years, accompanied by the development of increasingly sophisticated tool-use language and complex social learning. Each of these steps required specific selective pressures and genetic mutations, each a potential bottleneck or evolutionary dead end. The relatively late appearance of technologically capable humans on Earth is a striking observation. Our species Homo sapiens emerged only about 300,000 years ago. The development of agriculture and settled societies is a mere 10,000 years old. The Industrial Revolution, which gave humanity the capacity to alter the planet on a geological scale, is barely 250 years old. This means that for billions of years Earth hosted life, and for hundreds of millions of years it hosted complex multicellular life. Yet technologically capable intelligence emerged only in the very recent geological past. Why did it take so long? This late appearance provides strong arguments for the rarity or uniqueness of advanced life on Earth. One explanation is the Great Filter hypothesis, which posits that there are formidable obstacles or filters in the evolution of intelligent spacefaring life. If these filters are in the past, such as the emergence of eukaryotic cells, multicellularity, or complex intelligence itself, then we are rare because we have passed them. The long evolutionary journey to Homo sapiens, with its numerous bottlenecks and contingent events, suggests that many of these filters might indeed lie in our past. The debate between contingency and convergence in evolution is also relevant. Is evolution destined to produce intelligence, or is it highly contingent on specific chance events? The human path suggests a high degree of contingency. If the KPG extinction had not occurred, or if another lineage had dominated, human-like intelligence might never have arisen. This implies that our emergence is not a universal outcome but a specific historical accident within the vast possibilities of evolution. In the context of the Silurian hypothesis, which asks if a prior Earth civilization existed, the anthropic principle provides a powerful counterargument for its rarity. If advanced life is indeed rare and contingent, then the probability of it emerging twice on the same planet is significantly reduced. The anthropic principle, particularly its rarity interpretation, suggests that the specific chain of events leading to industrial intelligence is so finely tuned and so dependent on a long sequence of biological and planetary conditions that it might happen only once per habitable planet. The late appearance of humanity on Earth suggests that either the conditions were not right earlier in Earth's history, or the necessary evolutionary steps took an exceptionally long time and could easily have gone another way. This perspective provides a powerful argument against a prior terrestrial civilization, based on the specific evolutionary path and the unique planetary conditions that produced Homo sapiens. The exploration of exoplanets, worlds orbiting stars beyond our Sun, and the ambitious search for extraterrestrial intelligence, commonly known as SETI, offer a unique and profound parallel to the earthbound question of whether advanced civilizations existed millions of years before humans. The methodologies and challenges involved in detecting distant alien technologies, or technosignatures, across interstellar space can inform and provide context for our understanding of detecting subtle, deep-time civilizations here on Earth. Both inquiries grapple with the immense scales of time and space, the ambiguity of indirect evidence, and the profound implications of discovery or continued silence. The search for extraterrestrial intelligence has a rich history, dating back to early theoretical considerations and gaining scientific momentum with projects like OSMA in the 1960s. Traditionally, CT efforts have focused on radio astronomy, listening for intentional signals or beacons from advanced civilizations. The famous WOW signal detected in 1977 remains an intriguing but unconfirmed candidate for a non-terrestrial radio signal. While radio searches continue, they face immense limitations. Signals might be too weak, too brief, too directional, or simply not transmitted at the frequencies we are listening to. Optical CT, searching for laser pulses, offers another avenue but faces similar detectability challenges. More recently, the concept of technosignatures has broadened the scope of SETI. A technosignature is any observable sign or artifact that can be attributed to technology. This expands beyond intentional signals to include any indirect evidence of technological activity, whether purposeful or incidental. The rationale is that even if civilizations do not actively broadcast their presence, or if they are long gone, their technological footprint might still persist and be detectable across vast cosmic distances. The types of technosignatures scientists look for on exoplanets offer direct parallels to the potential evidence of ancient Earth civilizations. One key category involves atmospheric chemical imbalances. An advanced industrial civilization could release synthetic pollutants into its planet's atmosphere, such as chlorofluorocarbons or other complex molecules not typically produced by natural biological or geological processes. Detecting these unusual atmospheric compositions, or finding combinations of gases that are highly indicative of industrial activity, for example, high levels of oxygen alongside methane, which would normally react and disappear in a natural setting, could be a compelling technosignature. This is a direct parallel to the search for industrial byproducts and altered geochemical cycles in Earth's deep past. If we are looking for anomalous carbon isotope ratios or heavy metal pollution in ancient Earth sediments, it is because we understand how our own industrial activity changes planetary chemistry. Another potential technosignature is industrial waste heat. Large-scale energy consumption by a technologically advanced civilization would generate waste heat, which would be radiated into space as excess infrared radiation. In extreme theoretical cases, a civilization might build Dyson spheres or Dyson swarms, colossal megastructures designed to capture nearly all of a star's energy. Such structures would dramatically alter the light curve of a star and emit a very distinct infrared signature, making them detectable across interstellar space. While far less grand, even widespread urban development could potentially generate detectable heat signatures. Artificial illumination, such as persistent light sources from cities on the night side of a planet, could also be a technosignature. While challenging to detect with current technology, future telescopes might be able to resolve such light patterns on nearby exoplanets. Megastructures are a more ambitious class of technosignature. Beyond Dyson spheres, this could include orbital rings, planetary-scale constructions, or massive engineering projects designed for starlifting or planetary modification. Such structures would alter the gravitational field or the light reflected from a star or planet in ways that could be observed. The Kepler Space Telescope and its successor, TS, have already searched for unusual dimming patterns in stellar light that could indicate such structures. Incidental radio leakage from a civilization's communication networks, such as terrestrial television and radio broadcasts, continuously leaks into space. While these signals quickly fade over interstellar distances, they represent a form of technosignature. However, their detectability is limited by distance and time. Signs of asteroid mining or star system engineering might also be considered technosignatures. An unusually ordered asteroid belt or clear signs of resource extraction or material processing within a star system could point to advanced technological activity. Evidence of interstellar spacecraft or probes, while incredibly difficult to detect, would be definitive technosignatures. The challenges of detecting exoplanet technosignatures are formidable. The vast distances involved mean that signals weaken immensely over light years, and any information received is effectively light from the past, sometimes millions of years old. The signal-to-noise ratio is overwhelming, with natural astrophysical phenomena creating immense background noise. Our current technological limitations mean that our telescopes and analytical tools are not yet powerful enough to detect anything but the most extreme or closest technosignatures. Ambiguity is a constant problem. Distinguishing a natural phenomenon from a truly artificial one requires meticulous observation and analysis to rule out all known natural explanations. We also operate under assumptions that alien technology operates on principles somewhat analogous to ours, or that their biology leads to technology we can conceive. What if an alien civilization's technology is completely different, perhaps biological or quantum-based, leaving no familiar signature? Furthermore, if intelligent civilizations are rare or short-lived, as suggested by some great filter hypotheses, then our chances of detecting them are greatly reduced. The parallels between detecting exoplanet technosignatures and detecting deep-time Earth civilizations are striking and mutually informative. Both searches primarily rely on indirect evidence. Just as we do not expect to find intact alien spaceships or advanced alien cities on distant exoplanets, we do not expect to find intact ancient Earth cities or complex machinery from millions of years ago. Both searches focus on subtle, indirect chemical, physical, or geological anomalies. Our own human impact on Earth, the Anthropocene, is essentially our planet's technosignature. The altered carbon isotope ratios from fossil fuel burning, the pervasive microplastics in sediments, the distinctive radioactive isotopes from nuclear activity, and the rapid climate change we are inducing are all types of technosignatures. If an alien civilization were observing Earth from light years away with sufficiently advanced technology, these are precisely the kinds of indirect signals they might detect, providing evidence of a technologically active planet. This direct analogy highlights what exactly we should be looking for in Earth's deep past if a prior industrial civilization existed. The challenge of ambiguity is common to both quests. Just as it is hard to distinguish a natural geological event from an ancient industrial byproduct on Earth, it is hard to distinguish a natural exoplanet phenomenon from a technosignature. Both require a thorough understanding of natural processes to effectively rule out natural explanations for observed anomalies. The silent planet problem also applies to both. If an alien civilization dies out or ceases to be technological, its direct signals like radio broadcasts would cease. Only lasting technosignatures might remain. This is directly analogous to a vanished ancient Earth civilization. Both the search for technosignatures on exoplanets and the investigation into the Silurian hypothesis require multidisciplinary approaches. CT involves astronomy, planetary science, physics, and chemistry. The Silurian hypothesis draws on geology, paleontology, chemistry, and climate science. The insights from one field can directly inform the other. The time dimension is also critical in both. For exoplanets, we're always observing light from the past, potentially seeing a civilization that no longer exists or has advanced far beyond what we perceive. For ancient Earth, we are looking for physical records from the very deep past, records that have been subjected to millions of years of geological transformation. Both inquiries operate on vast timescales. The methodologies developed for CT can directly inform the Earthbound search. Refining detection methods for technosignatures on exoplanets helps us understand what kinds of signatures are considered most durable or detectable over immense distances. These might be the only types of signatures that could possibly survive geological time on Earth. CT also encourages us to expand our imagination beyond anthropocentric views, thinking about novel forms of technology and alien biology. This broader perspective helps avoid narrowly defining what an ancient Earth civilization might have looked like, or what kind of traces it might have left. Understanding the survivability of hypothetical alien technosignatures in a stellar system helps understand how long analogous Earth-bound signatures might persist in our own planetary system. The Drake equation, a probabilistic argument used to estimate the number of active communicative extraterrestrial civilizations in the Milky Way galaxy, also has relevance. One of its factors is the lifetime of a civilization. This directly relates to the probability of detection. If civilizations are inherently short-lived, either due to self-destruction or resource depletion, then both interstellar and deep-time terrestrial detection becomes much less likely. A continuous lack of technosignatures on exoplanets, after increasingly thorough searches, would strengthen the idea of rarity. Similarly, a continuous null result for ancient Earth, after rigorous geological investigation, would have significant implications for the Silurian hypothesis. The future of technosignature search on both fronts is promising. Upcoming telescopes and analytical techniques will improve detection capabilities for exoplanets, allowing for more precise atmospheric characterization and searches for megastructures. Simultaneously, advances in geological core analysis, seismic imaging, and geochemical modeling will improve our ability to detect subtle anomalies in Earth's deep past. The ongoing dialogue between these seemingly disparate fields of inquiry can lead to unexpected insights, pushing the boundaries of what we understand about life's potential across the cosmos and its long history on our own planet. The exploration of life in extreme environments on Earth, a field known as extremophile biology, has profoundly expanded our understanding of the conditions under which life can not only survive but thrive. Extremophils are organisms that flourish in physical or geochemical conditions that are considered hostile to most known forms of life, pushing the boundaries of what was once thought possible for biological systems. Their existence fundamentally broadens our definition of life and intelligence beyond our inherent carbon-based temperate zone bias, opening speculative avenues for how an ancient non-human civilization might have developed in environments vastly different from those fostering human life. For much of scientific history, it was assumed that complex life required moderate temperatures, neutral pH, abundant water, and atmospheric oxygen, much like the conditions on the surface of Earth today. However, discoveries over the last few decades have revealed a hidden world of microbial life adapted to survive and proliferate in environments previously thought to be sterile. These extremophils challenge our anthropocentric views and demonstrate the incredible adaptability of life. One major category of extremophils is thermophils and hyperthermophils, which thrive in high temperatures. Thermophils prefer temperatures between 40 and 80 degrees Celsius, while hyperthermophils flourish above 80 degrees Celsius, some even living at temperatures exceeding 100 degrees Celsius, such as around deep-sea hydrothermal vents. These black smokers on the ocean floor release superheated, mineral-rich water, creating an environment of extreme heat and pressure, yet they support vibrant ecosystems. The organisms here have evolved unique enzymes and proteins that remain stable and functional at these high temperatures, unlike most proteins which would denature or break down. The discovery of thermophiles suggests that life could have emerged and persisted in the early Earth, which was much hotter and more geologically active than today. It also implies the possibility of life deep within the Earth's crust, sustained by geothermal heat. Conversely, psychrophils are organisms adapted to extremely low temperatures, thriving in conditions below 15 degrees Celsius, down to below freezing point. These can be found in polar ice, deep ocean waters, permafrost, and glacial environments. They possess adaptations like antifreeze proteins that prevent ice crystal formation within their cells and maintain membrane fluidity at low temperatures. The existence of psychrophils suggests that life could flourish on icy moons like Europa or Enceladus, which have subsurface oceans, or have persisted on Earth during prolonged periods of global glaciation like the Snowball Earth events. Acidophils and alkaliphiles are extremophiles that thrive in extreme pH levels. Acidophils live in highly acidic environments, sometimes with a pH as low as 0, such as acid mine drainage sites or volcanic hot springs. Alkaliphiles prefer highly alkaline environments with a pH up to 12 or more, found in soda lakes or certain soil types. These organisms have evolved unique mechanisms to maintain a near-neutral internal pH, despite the harsh external conditions, often involving specialized membrane structures and highly stable enzymes. Halophils are organisms that flourish in environments with high salt concentrations, significantly exceeding that of seawater. These can be found in salt lakes, salt evaporation ponds, and underground salt mines. They have sophisticated mechanisms to maintain osmotic balance, preventing water from being drawn out of their cells by the high external salt concentration, often by accumulating compatible solutes internally. This broadens the definition of water availability, as life might be found in highly saline ancient oceans or subsurface brines. Piezophils, also known as barophils or extremophils, that thrive under extremely high pressures, such as those found in deep ocean trenches or deep within the Earth's crust. They have evolved adaptations in their proteins and cell membranes that allow them to function normally under pressures that would crush most surface-dwelling organisms. The discovery of vibrant ecosystems in the deepest parts of the ocean has revolutionized our understanding of life's resilience to pressure. Radio-resistant organisms are those that can withstand extremely high levels of radiation, far exceeding the lethal doses for humans. These microbes, such as Deinococcus radiodurans, have incredibly efficient DNA repair mechanisms that allow them to recover from severe radiation damage. This suggests that life could persist in environments with higher background radiation, perhaps on early Earth when radiation levels were higher, or near radioactive deposits. Xerophiles are organisms adapted to survive in extremely dry conditions, such as deserts or very dry soils. They employ strategies like forming spores or producing compounds that help retain water in their cells. Oligotrophs are organisms that can thrive in nutrient-poor environments, often characterized by extremely slow metabolic rates, such as those found in the deep subsurface or ancient rocks. The metabolic diversity of extremophils further expands our concept of life. While most familiar life on Earth relies on photosynthesis for energy and aerobic respiration for metabolism, many extremophils utilize alternative energy sources. Chemosynthesis, for example, allows organisms to derive energy from chemical reactions, such as the oxidation of hydrogen sulfide methane or iron. This forms the basis of entire ecosystems around hydrothermal vents in the deep ocean, completely independent of sunlight. This implies that life could exist and flourish in subsurface environments or deep oceans, entirely disconnected from surface energy sources. Anaerobic respiration, using electron acceptors like sulfates, nitrates, or iron compounds instead of oxygen, is also common among many extremophiles, and was likely the dominant metabolic strategy on early Earth before the atmosphere became oxygenated. Lithoautotrophs are organisms that derive their energy directly from inorganic compounds or rocks, further highlighting life's ability to extract sustenance from geological processes. The existence of a vast and largely unexplored deep biosphere, extending kilometers into the Earth's crust, populated by such organisms, further underscores life's incredible versatility. These discoveries have profound implications for defining life itself. Life is demonstrably more diverse and resilient than previously thought, capable of thriving in conditions once considered uninhabitable. The traditional habitable zone around a star, defined by the presence of liquid water on the surface, is significantly expanded when considering microbial life. The presence of subsurface liquid water or geothermal activity can render planets or moons habitable far beyond this conventional zone. Now, let us engage in speculation about how intelligent life might arise and develop in such extreme environments, forming an ancient non-human civilization. Their forms of intelligence and technology would be profoundly shaped by their unique surroundings. Consider a hypothetical subsurface civilization of thermophiles or piezophiles, living deep within the Earth's crust. They would be powered by geothermal energy or chemosynthetic processes, completely independent of sunlight. Their environment would be characterized by constant high temperatures and immense pressures. How would they communicate? Perhaps through complex patterns of vibrations within rock, using seismic waves as their language. Their technology would likely focus on geoengineering, such as creating and maintaining vast networks of deep tunnels, managing heat flows, or extracting specific minerals from the rock for energy or construction. Their tools and machinery would need to be incredibly resistant to heat and pressure, perhaps involving high-temperature superconductors or materials that can flow under immense pressure. Such a civilization might leave traces like anomalous seismic patterns, specific mineral extractions deep within the crust, or localized heat anomalies that cannot be explained by natural geological processes. These traces would be very different from surface structures and incredibly difficult to detect, requiring deep drilling or advanced seismic imaging. An oceanic civilization living in deep ocean trenches or highly saline seas might be composed of piezophiles or halophiles. Their environment would be characterized by high pressure and eternal darkness, potentially with unique chemical compositions. Communication might occur via sonar, intricate bioluminescent displays, or complex chemical signals released into the water. Their technology would focus on hydrodynamics, pressure resistance, and perhaps harnessing the unique chemical gradients of deep sea vents for energy. They might construct structures on the deep ocean floor or within the oceanic crust, though these would be highly susceptible to subduction and erasure by plate tectonics over millions of years. Their waste disposal might involve unique chemical alterations of ocean water or deposition of specific materials in deep trenches. Imagine an ice-world civilization existing under kilometers of ice on ancient Earth during a snowball Earth period, or on an icy moon with a subsurface ocean. These psychrophiles would need to generate their own heat. Their energy might come from geothermal vents, or the internal heat of the planet. Their technology would be centered on ice melting and refreezing, tunnel boring through ice, heat management and pressure resistance. They might build intricate subglacial structures or modify the ice sheets themselves. The traces they leave would be challenging to identify, as vast ice sheets naturally form and melt, altering their own structure. However, unique meltwater signatures, specific subglacial deposits, or anomalous heat flows could be potential indicators. While less relevant for Earth's deep past, the concept of atmospheric civilizations on gas giants further broadens the definition of life. Such beings would exist in dense atmospheres, perhaps as balloon-like organisms. Their technology would involve buoyancy control, atmospheric manipulation, and remote sensing. Their traces would be ephemeral atmospheric anomalies, even harder to detect than subsurface traces. The nature of intelligence in these extreme environments would not necessarily be human-like. It could be a form of collective intelligence, like a highly organized swarm, or an intelligence that operates on much slower timescales due to lower metabolic rates in cold or high-pressure environments. Their communication methods would differ significantly from ours, relying on seismic vibrations, subtle chemical releases, or light-based signals adapted to their specific media. Their technological needs and capabilities would be inherently shaped by their environment. For instance, a civilization in a high-pressure, high-temperature environment might develop advanced material science for survival, rather than for space travel or communication over vast distances. Detecting traces of such extreme civilizations poses immense challenges. Their environments are inherently difficult to access and study. The deep subsurface and deep ocean remain largely unexplored. Their techno-signatures would be fundamentally different from human ones, and thus harder to recognize or interpret as artificial. How would we identify a tool if it is designed for a high-pressure, high-temperature, acidic, or extremely cold environment, and then degraded over millions of years? The geological record for these extreme environments is often less accessible or more altered than surface records. For instance, crustal rocks from deep environments are typically heavily metamorphosed, erasing subtle features. These considerations highlight the need for extreme open-mindedness and a readiness to look for the truly unexpected in Earth's deep past. The vast majority of life discovered on Earth, from the simplest microbes to the most complex organisms, is carbon-based and relies on liquid water as a solvent. This pervasive fact has led to a strong bias in our search for life beyond Earth, assuming that life everywhere must fundamentally share these characteristics. However, engaging in highly speculative thought experiments about the possibility of non-carbon-based life forms and their potential for developing advanced civilizations is crucial for broadening the scope of detection methods, both in the cosmos and potentially for an ancient Earth. While such alternative biochemistries are currently theoretical, they challenge our assumptions about life's fundamental requirements. Carbon's unique versatility is central to Earth life's complexity. Carbon atoms can form 4 stable bonds, allowing them to create long, complex chains and intricate ring structures. This tetrahedral bonding configuration enables an immense molecular diversity, forming the backbone of all organic molecules like proteins, nucleic acids, DNA and RNA, carbohydrates, and lipids. These carbon-carbon bonds are stable enough to form large molecules, but also flexible enough to break and reform, allowing for the dynamic chemical reactions essential for metabolism and replication at moderate temperatures. Liquid water serves as the ideal solvent for this carbon chemistry. Its polarity, hydrogen bonding capabilities, and ability to dissolve a wide range of compounds facilitate the complex biochemical reactions necessary for life. Carbon is also relatively abundant in the universe, making it a plausible candidate for life's building block. Despite carbon's evident suitability, scientists have long speculated about alternative biochemistries, driven by the desire to expand the definition of life beyond terrestrial chauvinism. Silicon-based life is perhaps the most commonly hypothesized alternative due to silicon's chemical similarities to carbon. Like carbon, silicon is tetravalent, meaning it can form 4 bonds, and it is in the same group on the periodic table. Silicon is also far more abundant in the Earth's crust than carbon. However, silicon faces significant challenges as a basis for complex life. Silicon-silicon bonds are much weaker than carbon-carbon bonds, while silicon-oxygen bonds are much stronger. This means that silicon-based chains would be less stable in water and tend to form rigid, insoluble silicates, which are the building blocks of rocks rather than flexible organic molecules. Chemical reactions involving silicon would generally be much slower and less dynamic than carbon-based reactions, potentially hindering the rapid information processing and metabolic rates necessary for complex life. Furthermore, if silicon were to form polymers analogous to proteins, they would likely be solid and rigid, possibly making a silicon-based organism physically rigid and stone-like. Alternative solvents like liquid ammonia, very hot liquid silicon or sulfuric acid have been proposed for silicon chemistry, each with its own extreme environmental implications. Liquid ammonia-based life is another speculative alternative. Ammonia is chemically similar to water in some respects, capable of forming hydrogen bonds and dissolving many organic compounds. However, liquid ammonia exists at much colder temperatures, typically between -78 degrees Celsius and -33 degrees Celsius at standard pressure. Life in such an environment would operate at extremely slow metabolic rates due to the low temperatures. The types of compounds stable in liquid ammonia would also be very different from those stable in water, requiring entirely different biochemical pathways and molecular structures. Proteins and nucleic acids as we know them would not be stable in liquid ammonia. Sulfur-based life has been hypothesized to exist in extremely hot and highly acidic environments, such as those found on Venus or some volcanic regions on Earth. Liquid sulfur or concentrated sulfuric acid could potentially serve as a solvent. Sulfur atoms can form long chains similar to carbon, but these chains are generally less stable than carbon chains and more reactive. Life based on sulfur chemistry might involve very robust, slow metabolizing organisms adapted to corrosive conditions. Phosphorus-based life is another concept. Phosphorus is an essential element for Earth life, forming the backbone of DNA and RNA molecules and being crucial for energy transfer and ATP. It can form chains, but these are less stable than carbon chains and react readily with water. Therefore, phosphorus-based life would likely require extremely anhydrous or water-free environments to prevent rapid hydrolysis, making it highly unlikely on planets with significant liquid water. The idea of arsenic-based life briefly gained attention with the controversial claim of a bacterium, GFAJ1, that could substitute arsenic for phosphorus in its DNA. While this claim was largely disproven, the concept itself, of an element structurally similar to an essential element in Earth life serving a similar biological role, remains an intriguing theoretical possibility for alternative biochemistries. However, arsenic bonds are generally weaker than phosphorus bonds, and arsenic is highly toxic to most Earth life. Beyond specific elements, the fundamental requirements for any form of life must be considered. These generally include a system for information storage and replication, an analogue to DNA or RNA, a means of metabolism for acquiring and transforming energy, a way to compartmentalize and maintain internal stability, a cell-like structure, and the ability to adapt and evolve over time through natural selection. These principles might be universal, even if the chemical constituents differ. The evolution of complexity in non-carbon-based life presents significant challenges. Carbon's unique versatility allows for the rapid formation and reformation of complex stable structures at relatively moderate temperatures which is crucial for dynamic metabolic processes and rapid information processing. Alternative biochemistries often imply extreme temperatures or pressures, which tend to slow down reaction rates considerably. A slower metabolism might mean extremely slow evolutionary processes, potentially requiring far longer timescales for intelligence and technology to emerge, if at all. Speculating on non-carbon civilizations leads to fascinating possibilities for their physical forms, technology, and detectability. A silicon civilization, if it could exist, might be characterized by incredibly slow metabolism and perhaps immense timescales for its evolution and technological development. Physically, they might be robust and stone-like, possibly even immobile or moving very slowly. Their technology might involve the direct manipulation of minerals, geological engineering on a vast scale, or energy harvesting directly from Earth's internal heat. Their communication could be geological, using seismic waves, or involve very slow light signals. Traces left behind might include highly organized mineral structures that are thermodynamically unlikely to form naturally, widespread altered geological formations, or anomalous isotopic ratios of silicon or other non-carbon elements in specific layers of rock. These would be extremely difficult to differentiate from natural geology without a clear understanding of what constitutes artificial for such a biochemistry. An ammonia-based civilization would exist in very cold environments and would likely have a very slow metabolism. Their technology might focus on heat generation and management to create suitable internal environments, cryogenics, or subtle chemical manipulation specific to ammonia-based compounds. Traces could include unique cryostructures formed from frozen ammonia or altered atmospheric chemistry that remain stable at very low temperatures. A sulfur-based civilization might exist in extremely hot and corrosive environments. Their technology would involve extreme material science for survival in their harsh surroundings and the manipulation of sulfur compounds for energy or construction. Their traces could manifest as anomalous sulfur mineral deposits or unique chemical signatures related to their biochemistry in ancient strata. Detecting traces of non-carbon civilizations, whether on other planets or potentially in Earth's deep past, faces even greater hurdles than detecting carbon-based ones. First, recognizing life itself, even before civilization, would be a massive challenge. Its waste products, biological signatures, and even the fundamental chemical components of its cells would be entirely unfamiliar. Second, recognizing technology would be exponentially harder. We look for carbon isotope anomalies as industrial waste. What would a silicon civilization's industrial waste look like? Perhaps anomalous silicon isotopes or specific non-naturally occurring silicon compounds. Our current search methods are fundamentally biased towards carbon-water life, reflecting our own biochemistry. This anthropocentric bias limits our ability to conceive of, much less detect, life or technology that operates on entirely different chemical principles. The biggest challenge lies in the unknowable unknowns. We might not even be able to conceive of the physical forms, metabolic processes, or technological expressions such life could take, making it exceedingly difficult to know what to search for. For the Silurian hypothesis, the possibility of non-carbon life significantly broadens the scope of what an ancient Earth civilization might have been. It implies that life and intelligence could have arisen under environmental conditions that we currently deem inhospitable, using biochemistries we can barely imagine. While this expands the possibilities, it simultaneously makes the search for traces exponentially harder, as we would not know what specific chemical, mineralogical, or isotopic signatures to target. It underscores the need for extreme open-mindedness, cross-disciplinary research, and a willingness to explore theoretical frontiers far beyond our current understanding of life.